So, here's something that might catch you off guard, lying there in the dark. Right now, in this exact moment, your brain is running thousands of small calculations just to keep you sitting there, or lying there, breathing evenly, aware of the weight of the blanket resting on your legs. It is measuring distances between your body and the mattress beneath you, adjusting second by second without you ever giving the instruction. It is estimating time intervals between breaths, timing the gap between one inhale and the next, keeping the rhythm steady even while your attention drifts somewhere else entirely. It is doing arithmetic on light and sound, even in a dark, quiet room. Even with your eyes closed, just to confirm that nothing has changed since a few seconds ago, that the shape of the room is still the shape of the room, that the sound of the house settling is nothing more than the house settling. You have never been taught most of this. Nobody sat you down and explained the mathematics of balance, or timing, or spatial awareness. Your nervous system simply does it, silently, continuously, the way it has for your entire life, the way human nervous systems have done it for as long as there have been humans lying still in the dark, trying to fall asleep. Think about that for a moment, slowly, without any pressure to fully follow it. Somewhere in your body, right now, tiny structures in your inner ear are measuring the tilt of your head against gravity, converting that tilt into a signal, comparing it constantly against a kind of internal baseline, all so that you know, without having to think about it, which way is up. That is a form of measurement. That is a form of comparison. That is, in its own quiet biological way, mathematics, running underneath conscious thought, the same way it has run underneath every human body for as long as bodies like yours have existed. Tonight, we're going to go through all of mathematics. Not a single formula pulled out and explained in isolation, not a dry list of names and dates to memorize, but the actual long, slow human story of it, from the very beginning, all the way through to how it quietly runs underneath almost everything you touch, everything you use, everything happening in the room around you at this very moment. We're going to trace how counting became numbers, how numbers became patterns, how patterns became proof, and how proof, once it existed, became an entire way of understanding the universe, a way of being certain about something without needing to see all of it, or touch all of it, or measure all of it by hand. By the end of tonight, whether you hear every word of it, or drift away somewhere in the middle and hear only fragments, you will understand not just what mathematics is, but why it grew the way it did. You will understand that it was not handed down, complete and finished, from some singular brilliant mind. It was built piece by piece, by real people, in real places, over thousands of years, each one solving a problem the last person could not quite finish, each one standing on ground someone else had quietly, carefully prepared for them, often without knowing it. A scribe pressing symbols into wet clay in an ancient river valley did not know that a philosopher across the sea would take that same basic idea of number and ask, for the first time, why it worked. That philosopher did not know that his questions would eventually lead somewhere strange and unsettling, a discovery that broke apart an entire belief system built on numbers being simple and orderly. And none of them knew that centuries later, all of it, every piece of it, would somehow end up folded into the device resting near your bed tonight, quietly calculating where you are on the surface of the earth while you sleep. That is the shape of tonight. Not a straight line from ancient to modern, but something more like a very long, patient river, picking up new tributaries along the way, widening, slowing, occasionally splitting into separate channels that circle around, unexpectedly, and rejoin each other again much later. We will move slowly through it, the way water moves slowly, without hurry, without any need to reach the end quickly. If you fall asleep somewhere along the way, that's perfectly fine. That is, in fact, the entire point of tonight. There is no test waiting for you at the end of this. No quiz. Nothing you are required to remember by force. Nothing you need to hold on to with effort. This is not a lecture you have to sit upright for, taking notes, worried about missing something important. You can let your attention rise and fall, the way your breathing rises and falls, following it closely for a while, then losing it, then finding it again a little later, and none of that will matter. The ideas will still be here if you want to come back to them tomorrow, or the night after that, or many nights from now. And even if you don't consciously follow every sentence tonight, even if whole stretches of this simply wash past you while your mind is already halfway into sleep, something of it will still settle into you anyway, quietly, the way most things that happen to us while we are drifting off seem to settle in without our permission or our attention. So let yourself get comfortable now, if you haven't already. Let your shoulders drop away from your ears, releasing whatever small tension has been sitting there, unnoticed, for who knows how long. Let your jaw unclench, your tongue rest heavy and loose in your mouth, your hands go soft and open rather than closed. There is nowhere else you need to be right now, and nothing else you need to be doing, except exactly this, lying here, letting a very old story be told to you slowly, one small piece at a time. And let's start a very long time ago, long before numbers had names, long before anyone had written anything down at all, before there were cities, before there was writing, before there was anything we would recognize today as civilization, there was only counting, in its most basic, most physical form, the kind of counting that does not need language, does not need symbols, does not need anything at all except a mind noticing that one thing is different from many things, and many things are different from none. This need to count, to know how many, is older than almost anything else we consider distinctly human. It is older than farming, older than permanent settlements, older, even, than most of what we would call organized society. It comes from something much more basic than commerce or record-keeping. It comes from survival itself. How many animals moved past the entrance to the shelter tonight, and is that more or fewer than usual? How many days have passed since the last full moon, and is it close to time for something important to happen again, some seasonal shift the body has learned to expect? How many people are gathered together on this side of the hill, and is that enough people, or not quite enough, compared to whatever might be gathered on the other side? These are not abstract questions. They are questions about safety, about resources, about whether tonight is a night to worry, or a night to rest easy, and answering them required something our earliest ancestors had to slowly, carefully invent, an act so basic we barely think of it as invention at all anymore, the idea that a physical mark, made in one place, could stand in for a quantity that existed somewhere else, in memory, or in the world, or simply in the moment. A single scratch could mean one thing. A second scratch, added carefully beside the first, could mean one more thing than that. This is the seed of everything we're going to walk through tonight, the entire, enormous structure of mathematics that followed. Not a formula, not an equation, just a mark, standing in for a quantity, made by someone, somewhere, long before anyone thought to ask what a number actually was, or why marks like this seemed to work so reliably, every single time, for counting anything at all. That question, why it worked, would not arrive for tens of thousands of years. But the marks themselves, the quiet, patient act of representing something invisible, using something visible, something you could see and touch and return to later and trust to mean the same thing it meant before, that came first. And it is exactly where we're going to begin, slowly, in just a moment, in a cave, with a bone, and a very old, very simple set of careful notches. Before there was writing, before there were cities, before there was anything we would recognize as civilization, there was counting. Not mathematics yet, not in any formal sense, just the basic human need to know how many. How many animals moved past the edge of camp this morning? How many days since the moon was last full and round in the sky? How many people are gathered in this group, and is that more or fewer than whatever group might be gathered on the far side of the hill? This need is older than recorded history itself, older than anything we might call a society, and we know it is older because of a small, quiet object found in a cave in the Lubombo Mountains, along the border of what is now Eswatini and South Africa. It is a simple thing, really, A piece of baboon fibula, a leg bone, worn smooth by time, with 29 distinct notches carved into it, in a single careful row. It is somewhere between 43,000 and 44,000 years old. Nobody today knows exactly what was being counted. Maybe days. Maybe the phases of the moon, tracked one notch at a time across a full cycle. Maybe something else entirely, something we no longer have any way of guessing. But someone, tens of thousands of years before the first pyramid was ever imagined, sat down with a bone and a sharp stone and made a single mark, and then made another mark beside it, and then another after that, keeping a slow, patient tally going, notch by notch, for reasons we can only imagine now, in the quiet dark, so many thousands of years later. That is the first mathematics. Not numbers written down in the way you would recognize them, not symbols, not equations, nothing like what you might remember from a classroom. Just the idea, simple and enormous at the same time, that a physical mark could stand in for a quantity. That you could take something invisible, an amount, a count, a number of days, or a number of animals, and give it a visible form, something you could see and touch and return to later, and trust to still mean the same thing it meant before. That single idea, quiet and unassuming as it sounds, is the seed everything else tonight will grow from. A similar object, called the Ishango bone, was found much later by archaeologists, near the headwaters of the Nile, in what is now the Democratic Republic of Congo. It is dated to around 20,000 years ago, younger than the Lubombo bone, but still almost unimaginably old. Its notches are arranged in small clusters, grouped together in ways that some researchers believe show early signs of something more organized than a simple tally, perhaps an early attempt at multiplication, or perhaps a basic calendar, tracking some repeating cycle in the sky or the seasons. Other researchers are more careful, more cautious, and think it is possible we are reading structure into what was, in the end, simply a tally, no more complicated than the marks in the Lubombo bone. We may never know for certain which reading is correct, but either way, the pattern that matters is the same pattern, long before agriculture, long before permanent settlements, before villages, before anything like a town or a city. Humans were already reaching outside their own minds to hold on to number, taking something that existed only as a thought, an idea, a private sense of how many, and giving it a physical shape outside the body, something that could outlast a single memory, something that could be checked again later, by the same person, or perhaps even by someone else entirely. The real turning point in this story, the moment counting truly became something larger, came much later, around 5,000 years ago, in the region between the Tigris and Euphrates rivers, an area historians now call Mesopotamia, roughly where the country of Iraq sits today. This is where the Sumerians lived, and the Sumerians had a problem that a simple tally, a row of notches on a bone, could never solve for them. They were not just counting days or animals anymore. They were running something closer to what we would recognize as an economy. They had grain stores that needed tracking, temples that collected offerings from the surrounding villages, workers who needed to be paid, often in barley, sometimes in wool, trade routes that stretched outward across the wider region, carrying goods back and forth between distant settlements. You cannot run something as complex as that, using notches cut into bone. You need a system that can represent large numbers efficiently, a system that can be recorded, stored safely, checked again later when a dispute arises, and, just as importantly, a system that different people, in different places, could read the exact same way, without confusion. Their solution began, gently enough, with small clay tokens, simple shapes, cones, spheres, flattened discs, each different shape standing in for a different quantity of a different good. A small cone might represent one modest measure of grain. A sphere, larger and rounder, might represent a bigger measure. These tokens were often sealed away inside hollow clay balls, called bulle, functioning as a kind of early receipt, proof of what had been exchanged or promised. But sealing the tokens away created an obvious, practical problem. Once a bulla was closed and dried, you could not see what was sealed inside it without breaking the whole thing open. destroying the record in order to check it. So, slowly, scribes began pressing the tokens into the soft outer surface of the wet clay, before sealing the bulla shut, leaving a clear impression behind, a visible record of exactly what the bulla contained, right there on its surface, for anyone to read without opening it. And then, in a step so simple that it is almost easy to overlook how significant it truly was, someone, whose name we will never know, realized something quietly important. If the impression pressed into the outside of the clay already told you everything you needed to know about what was inside, then you did not actually need the tokens themselves at all anymore. You could simply press, or scratch, symbols directly into a flat tablet of clay and skip the tokens entirely. This shift happened somewhere around 3400 to 3100 BCE, and it stands as one of the most important, most quietly transformative moments in the entire history of mathematics, because it marks the shift away from physical counting objects, things you could hold in your hand, and toward abstract written symbols instead, marks that carried meaning purely by agreement, purely by shared understanding. A number, from this point forward, was no longer a pile of small clay shapes you could count out on a table. It was a mark, a sign, something that could represent a quantity without needing to physically contain it, or resemble it, or hold its weight in your palm. This early Sumerian system gradually evolved into what we now call cuneiform numerals, small wedge-shaped marks, pressed carefully into wet clay using a cut-reed stylus, and from there, it evolved into something else worth sitting with for a moment tonight. Something genuinely different from what you likely grew up using. A base 60 number system, known formally as sexagesimal. This might sound strange to your ear, since you almost certainly grew up counting in groups of 10, using what is called base 10, most likely because human beings happen to have 10 fingers to count on. But base 60 had its own quiet logic, its own kind of elegance. 60 divides evenly by 2, by 3, by 4, by 5, by 6, by 10, by 12, by 15, by 20, and by 30. That is an extraordinary number of clean, whole divisions for a single base to offer, and it made the system remarkably well suited to the kind of fraction-based accounting that trade and taxation and the careful division of shared resources required, again and again, across an entire civilization. And here is something worth noticing, quietly, as you lie there tonight, breathing slowly. You are still living inside this very same system every single day of your life, without ever really noticing it. 60 seconds make up a minute. 60 minutes make up an hour. 360 degrees make up a full circle. All of that, every bit of it, traces directly back to Sumerian mathematics and to the Babylonian mathematics that followed and expanded upon it 4,000 years ago, in a river valley that no longer exists today in anything like the form it once had, and yet somehow, quietly, its counting system has outlived the empire itself, outlived the language, outlived the clay tablets, and settled instead into the reed of every clock, on every wall, in every room, including perhaps the very room you are lying in right now. The Babylonians, who inherited Sumerian mathematics and slowly expanded it further, contributed something else worth understanding carefully, something that deserves a little more of your attention before we move forward tonight. They developed what is called a place value system, meaning that the position of a symbol, where it sat, mattered just as much as its shape did. In our own base 10 system today, the digit 5 means something different depending entirely on where it sits. Written in the number 50, it means something different than when it is written in the number 500, purely because of its position, purely because of what sits around it. The Babylonians developed a version of this same insight almost 2,000 years before it would appear again in India, in roughly the form we still use ourselves today. It was not, admittedly, a perfect system. For a long stretch of Babylonian history, they had no symbol at all, for zero, no clean way to mark an empty position within a number. This meant that context alone had to tell a reader whether a particular symbol meant 1 or 60, or perhaps 3,600, depending entirely on how the surrounding symbols were arranged. Imagine, for a moment, writing an entire sentence with no spaces between the words at all, relying completely on the reader's own judgment to figure out where one word quietly ends and the next one begins. That was Babylonian arithmetic, for a very long stretch of time. Workable, certainly, functional enough to run an empire, but genuinely, unavoidably ambiguous. One particular Babylonian clay tablet deserves a slower, more careful mention here, because it shows, quietly and convincingly, just how advanced their mathematics had already become, long before Pythagoras was ever born. Known today as Plimpton 322, named after the collector who once owned it, and dated to somewhere around 1800 BCE, this tablet contains 15 careful rows of numbers that, when patiently decoded by modern scholars, turn out to be an organized list of numbers satisfying the very same relationship we would later come to call the Pythagorean theorem. Sets of 3 whole numbers, where the first 2, each multiplied by itself, sum together to equal the third, also multiplied by itself. Whoever produced this tablet was almost certainly a scribe, working within a long scholarly or administrative tradition of applied mathematics, and they were not simply stumbling onto these particular number sets by accident. The careful, deliberate pattern in how the rows are ordered strongly suggests a systematic method for generating them, more than 1,000 years before any Greek mathematician would eventually sit down and write out a formal proof explaining why such number sets must always exist in the first place. That is a useful thing to hold on to quietly as we drift further into tonight's story. The gentle reminder that knowing a mathematical fact works and understanding why it must always work are 2 genuinely different achievements, and that different civilizations, working entirely independently of one another, separated by centuries and by vast distances, often reach that first kind of knowledge long, long before anyone reaches the second. So, here it is, plainly, right at the start, before we go any further into the actual history. You have permission to fall asleep, not permission you need to ask for, not permission that depends on how well you've been paying attention so far, but permission that was already yours the moment you pressed play. If your eyes are heavy right now, let them close. If your mind is already drifting somewhere else, following the sound of my voice without quite following the words, that's fine too. That's not a failure of listening. That's the entire point of listening to something like this. Most of what you were taught about learning, growing up, probably came with an unspoken rule attached to it. Pay attention or you'll miss something. Stay focused or you'll fall behind. Sit up straight, keep your eyes open, keep your pencil moving. That rule made sense in a classroom, where the goal was to prepare you for a test on a specific day, at a specific hour, where missing a detail really could cost you something. But that rule does not belong here, in this room, at this hour, with the lights already low and your body already sinking into whatever you're lying on. Tonight has no test. Tonight has no deadline. Tonight has no one checking whether you can repeat back what was said an hour ago. The only thing tonight actually asks of you is that you let yourself rest, and if understanding happens along the way, quietly, in the background, without effort, that's a kind of bonus, not the requirement. So let's slow down here for a moment, because this deserves to be said clearly, and probably more than once, since it runs against so much of what you've likely internalized without ever really examining it. You do not need to catch every word. You do not need to remember the order things happened in, or the names of the people involved, or the specific numbers and dates that get mentioned along the way. None of that is the goal tonight. The goal is something much simpler and much older than any classroom. The goal is for your body to settle, for your breathing to slow on its own, for the small, restless part of your mind that keeps turning over the day behind you to finally loosen its grip and let go. If some of the history and the ideas happen to sink in while that's happening, wonderful. If they don't, if you're asleep within the next 10 minutes and miss almost everything that follows, that is not a loss. That is simply what was supposed to happen. There is something worth understanding about how a mind works right before sleep, something that might make this permission feel a little more solid, a little more trustworthy, rather than just a kind, comforting thing to say. In the last stretch before sleep actually arrives, your brain doesn't process information the way it does during the middle of a busy afternoon. Focus loosens. Attention drifts in and out, the way a boat drifts when you stop rowing. Still moving, just no longer being steered with any real effort. Words start to blur slightly at the edges. Sentences slide past without being fully passed, and that is completely normal, completely expected, and not something to fight against. If you notice yourself losing the thread of what's being said, that is not you doing something wrong. That is simply your nervous system doing exactly what it's supposed to do at this hour, stepping back from sharp, effortful focus and easing into something looser, softer, and far more restful. You might drift off completely somewhere in the next few minutes, wake slightly sometime later, catch a sentence or two, and drift off again. That's fine. You might make it 20 minutes in before sleep finally takes you, or 2 minutes, or you might already be halfway gone right now, barely holding on to these very words. All of those outcomes are exactly right. There is no version of tonight where you are listening incorrectly. There is no version where you should have stayed awake longer, or focused harder, or tried to remember more. The only wrong way to listen to this would be to lie there anxious about whether you're listening the right way, and that anxiety itself is the one thing worth gently setting down before we go any further. Let yourself unclench for a moment, if you can. Not in a big, dramatic way, nothing that requires effort or concentration, just a small, quiet release. Let your jaw loosen. Let your shoulders drop a little further away from your ears than they were a minute ago. Let your hands go soft wherever they're resting. None of this needs to happen quickly, and none of it needs to happen completely. Even a small amount of loosening is enough. Your body already knows how to do this. It has been doing it in one form or another every single night of your life, long before you ever thought about it consciously, and it will keep doing it tonight, with or without your help, simply because you're lying still, in a quiet room, listening to a calm and steady voice. Here is something else worth saying plainly, since it tends to ease a particular kind of worry that shows up right around this point in the night. You are not going to lose anything by falling asleep early. There is no thread here that unravels if you're not awake to hold on to it. Everything in tonight's explanation, every idea, every name, every century we pass through, will still be exactly where it is if you ever want to come back to it tomorrow night, or next week, or a year from now. Mathematics itself works this way too, in its own quiet fashion. A proof written down 2,000 years ago is still sitting there today, fully intact, unchanged, waiting patiently, not going anywhere, not needing anyone to check on it constantly to remain true. In a much smaller, much gentler way, this recording works the same way. It will still be here. It is not going anywhere either. So if you fall asleep in the next few minutes, that's the plan working exactly as it should. If you make it much further than that, and find yourself still awake an hour from now, gently following along as we move through history, that's also the plan working exactly as it should. There is no correct amount of tonight that you're supposed to hear. There is no minimum. There is no version of you tomorrow morning who did this wrong. You cannot fail at resting. You cannot fail at listening to a voice in a dark room while your body does what bodies have always done at this hour, slowing down, softening, letting the day finally end. Let's say this one more time, differently, since repetition tends to help right around the edge of sleep, when a single hearing of something often isn't quite enough for it to fully land, but hearing it again, in slightly different words, has a way of settling it more deeply. The way a fact told to you twice in childhood tends to stay with you longer than a fact told only once. You have nowhere to be right now except exactly where you already are. You have nothing to accomplish tonight except the thing your body is already doing on its own, without needing instructions, without needing effort, without needing you to do anything at all except stay still and let it happen. If your attention wanders off somewhere in the middle of a sentence about ancient Sumeria, or Egyptian floodwaters, or Greek philosophers arguing on a beach, let it wander. It will come back if it wants to, and if it doesn't, that's fine too. Nothing about tonight depends on your full attention arriving right on cue and staying there. There is a particular kind of relief in being told, clearly and directly, that you don't have to try. So try to hear this permission the way you might hear a held breath finally being let out. You don't have to try to stay awake, and you don't have to try to fall asleep either, since trying at either one usually makes both harder. You simply have to lie there, breathing, listening a little or a lot, and let whatever happens next happen on its own timeline, at its own pace, without your interference. Sleep tends to arrive most easily exactly when it's not being chased, the way a shy animal tends to come closer only once you've stopped watching it directly, once your attention has softened into something calmer, something that isn't demanding a particular outcome. So, one more time, plainly, because it bears repeating as often as it takes to actually sink in tonight. If you fall asleep somewhere along the way, that's perfectly fine. That's the point. The ideas will still be here if you want to come back to them. There is no rush anywhere inside tonight, no urgency hiding behind any of it, nothing waiting to be missed. Whatever you take in, whatever slips past you unheard, whatever half-sentence you catch just before drifting off completely, all of it is enough. Now let your eyes close, if they haven't already, and let's begin a very long time ago, slowly, quietly, with nowhere in particular that we need to be. Let's start a very long time ago, before numbers even had names, before anyone had written a single word down anywhere on earth, before there was writing, before there were cities, before there was anything you or I would recognize as civilization, there was counting. Not mathematics yet, not in any formal sense, just the plain, practical human need to know how many. How many sheep left the pen this morning, and did all of them come back? How many days since the moon was last full and round? How many people are standing in this group, and is that more than the group waiting on the other side of the hill? This need is older than recorded history itself, older than farming, older than permanent shelter of any kind, and we know this not because anyone wrote it down, but because someone left behind a small, quiet piece of physical evidence, a single object that has survived, against enormous odds, for tens of thousands of years. It's a bone. A leg bone from a baboon, found in a cave in the Lebombo Mountains, along the border of what is now Eswatini and South Africa. Carved into it, in a single row, are 29 distinct notches, cut with a sharp stone, by someone whose name we will never know, whose face we will never know, whose language we will never even be able to guess at. This bone is dated to somewhere between 43,000 and 44,000 years old. Say that number slowly to yourself for a moment. 43,000 years. That is not close to the pyramids. That is not close to the first cities, or the first farms, or the first written word. It is so far back that almost nothing else from that person's daily life survives at all. No house, no clothing, no tool but this one. And yet this one small, deliberate act remains, waiting patiently in the dark of that cave for tens of thousands of years, until someone finally found it. Nobody knows for certain what those 29 notches were counting. It might have been days. 29 is close to the length of a lunar cycle, the stretch of time between one full moon and the next, so it's entirely possible this was an early calendar, a way of keeping track of the sky. It might have been something else entirely, something we have no way of guessing at now, some private tally that meant something only to the person who carved it. We will likely never know for certain, but here is what we do know, and it's worth sitting with for a moment, because it's the true beginning of everything we'll walk through tonight. Someone, in that deep, quiet stretch of prehistory, sat down with a bone and a sharp stone and made a mark, and then made another mark, and kept the tally going, night after night or day after day, patiently, one notch at a time. That is the first mathematics. Not numbers written down the way we'd recognize them now, not symbols with names, just the simple, quietly radical idea that a physical mark could stand in for a quantity, that you could take something invisible, an amount, a count, a number of days, and give it a shape you could see and touch and come back to later. Before this, a quantity only existed in the moment it happened in. You saw 5 sheep leave the pen, and then that moment passed, and the memory of it faded the way memories do. A notch on a bone changes that completely. It lets a quantity outlive the moment it described. It lets someone, tens of thousands of years later, hold that same bone and see, still visible, still countable, exactly what someone else once counted, long before either of them existed to the other. There's a second bone worth knowing about tonight, found much farther north, near the headwaters of the Nile River, in what is now the Democratic Republic of Congo. It's called the Ashango bone, and it's a little younger than the Lebombo bone, dated to roughly 20,000 years ago, though even that is still an almost unimaginable stretch of time before anything we'd call civilization existed. The notches on this one are more complicated. They're arranged in distinct groups rather than a single simple row, and some researchers who have studied it closely believe these groupings might show something more than a basic tally, possibly an early attempt at multiplication, or perhaps another kind of calendar, tracking something in the sky across a longer stretch of time. Other researchers are more careful about this, more hesitant to read too much structure into marks that might simply be a tally after all, made by someone counting something ordinary, something we'll never be able to name. Both possibilities stay open. That uncertainty itself is worth sitting with tonight, because so much of the very earliest human history is like this, a handful of physical clues and a great deal of careful, humble not knowing. But whichever explanation turns out to be closer to the truth, the underlying pattern is the same one we saw with the Lebombo bone, and it's worth saying plainly, because it will come up again and again tonight in different forms. Long before agriculture, long before permanent villages or cities, long before anyone had domesticated a single animal or planted a single deliberate row of crops, human beings were already doing something quietly profound. They were externalizing number, taking something that only existed as a fleeting idea inside a single mind and giving it a physical form outside the body, something durable, something that could be looked at again, shared with someone else, trusted to still be there the next day. Think about what that actually requires, for a moment, since it's easy to move past this too quickly. It requires noticing that quantity is a real property of the world, separate from whatever specific thing is being counted. 5 sheep and 5 days have nothing whatsoever in common, except this one abstract fact, that they are both, in some sense, 5. To notice that, to feel that a fiveness exists independent of sheep or days or fingers or stars, and that this fiveness can be marked down, is a genuinely remarkable leap of thought, even though it likely happens slowly, gradually, across many minds, over an almost incomprehensible stretch of time, rather than arriving all at once in a single flash of insight from any one person. You don't need to remember either of these bones by name. If the details slip away from you in the next few minutes, that's completely fine. That's expected. That's simply what tends to happen at this hour. What's worth carrying forward, even loosely, even half-formed, is just the feeling underneath it. That mathematics didn't begin in a classroom, or with a formula, or with anything that looks the way you might picture mathematics looking. It began in the dark, much like this room is dark right now, with someone alone, patient, making one small mark, and then another, slowly turning something invisible into something they could hold on to. Let that settle for a moment. There's no need to do anything with it. No need to picture the exact shape of a baboon's leg bone, or count out 29 notches in your mind, or worry about which cave was in which mountain range. Just let the shape of the idea rest there quietly, the way the bone itself rested quietly in that cave, undisturbed, for tens of thousands of years, waiting. From here, across many more thousands of years, this same simple impulse, the desire to mark down a quantity and keep it, would slowly grow. It would move from notches on bone to small clay tokens, shaped like cones and spheres, used to track grain and goods in the very first cities. It would move from those tokens to marks pressed directly into wet clay, the earliest true writing anywhere in the world, born not from poetry or storytelling, but from something far more practical, the need to remember exactly how much grain was owed and to whom. We'll walk through that part of the story soon, slowly, the way we're walking through everything tonight, one quiet step at a time. But for now, just rest in this early moment. Somewhere, a very long time ago, in the dark, someone made a mark because they wanted to remember something. That is where all of this begins. Not with certainty, not with grand structures, not with anything close to what you might picture when you hear the word mathematics. Just with a single small act of attention, a person chooses to notice and to keep. And from that one quiet act, repeated by countless different people, in countless different places, across an almost unimaginable stretch of time, everything else we'll talk about tonight would eventually, slowly, patiently grow. The real turning point came a very long time after that first bone, with its careful notches, but still further back than most people imagine. Somewhere around 5,000 years ago, in the land between two rivers, the Tigris and the Euphrates, in what is now Iraq, a civilization arose that historians call Mesopotamia. It was here, among the Sumerians, that counting stopped being a private, personal act, a single person tracking days or sheep, and became something else entirely, something that an entire society depended on to function. The Sumerians had built something the world had not quite seen before, in this particular form. They had cities, real cities, with temples and granaries and workers who needed to be paid, and trade routes stretching out across the land in every direction. And a city like that runs on something that a simple tally on a bone can never provide. It runs on an economy. Grain had to be stored and measured. Offerings had to be collected at the temples and recorded. Workers needed to be paid, often in barley or in wool, and someone needed to remember exactly how much each person was owed, and exactly how much had already been given. You cannot run something this complicated with notches cut into a bone. A bone can tell you how many days have passed. It cannot tell you how many measures of grain are owed to 40 different workers, across a dozen different storehouses, over the course of an entire growing season. So the Sumerians needed something new. They needed a system that could represent large numbers efficiently, a system that could be written down, stored safely, and checked again later, by someone other than the person who had made the record in the first place. They needed numbers that different people in different parts of the city could read the exact same way, without any confusion. This was the problem sitting in front of them, quietly, patiently, and it would push them toward one of the most important inventions in the whole of human history. Their first solution was simple and almost playful in its own way. Small clay tokens shaped like cones and spheres and flat discs, each shape standing for a different quantity of a different good. A small cone might represent one small measure of grain. A sphere might represent a larger measure. If a merchant needed to record a transaction, he could gather the right tokens together, the right shapes in the right quantities, and that small collection of clay pieces would represent, physically, exactly what had been exchanged. But tokens on their own have an obvious weakness. They can be lost, they can be scattered, they can be swapped out and no one would necessarily know. So the Sumerians came up with a clever solution. They would seal a set of tokens inside a hollow ball of clay, called a bulla, closing them up inside, safe and unchangeable, as a kind of receipt. If a dispute ever came up later about how much grain had actually been promised or delivered, you could break open the bulla and see, with your own eyes, exactly which tokens were sealed inside, settling the matter for good. There was still a problem hiding inside this solution, though, and it's worth sitting with for a moment, because the way it was solved changed everything that came after. Once a bulla was sealed shut, you could no longer see what was inside it without breaking it open. And breaking it open destroyed the very record you were trying to protect. So scribes began doing something simple, almost obvious in hindsight, but genuinely clever at the time. Before sealing the tokens inside, they pressed each one into the soft, wet clay on the outside of the ball, leaving a clear impression of its shape on the surface. Now you could look at the outside of a sealed bulla and see, right there in the clay, exactly what was sealed inside, without ever needing to break it open at all. And then came the moment that mattered most, the small, quiet realization that changed the direction of the entire story. If the impression on the outside already told you everything the tokens inside could tell you, then, in a sense, you didn't need the tokens at all anymore. You could skip the tokens completely and simply press or scratch the symbols directly onto a flat tablet of clay. No hollow ball, no hidden tokens sealed away inside. Just a flat, open record, marked clearly on its surface for anyone to read. This happened somewhere between about 3,400 and 3,100 years before the Common Era, and it's genuinely one of the most important moments in the whole story of mathematics, quiet as it might sound. It marks the shift away from physical counting objects, things you could hold in your hand, and toward abstract written symbols, marks that stood for a quantity without containing it, without being it. A number was no longer a pile of little clay shapes you had gathered together. It was a sign, a mark, something you could write down once and read again and trust, without needing anything physical behind it at all. This system continued to grow and change over the centuries that followed, evolving into what we now call cuneiform numerals, small wedge-shaped marks pressed into wet clay using a cut reed as a stylus. And along with this new way of writing numbers came something else, something that might sound unusual to you at first, lying there tonight, but that has quietly shaped your entire life without your ever really noticing it. The Sumerians, and later the Babylonians, who inherited and expanded their mathematics, counted using a base of 60 rather than the base of 10 most of us grew up with. This might sound strange. We count in groups of 10, most people assume, simply because we happen to have 10 fingers. But base 60 had its own kind of logic, its own kind of usefulness, and it's worth understanding gently, since it explains something about your own daily life that you've probably never thought to question. 60 divides evenly by an unusually large number of smaller numbers. It divides evenly by 2, by 3, by 4, by 5, by 6, by 10, by 12, by 15, by 20, and by 30. That's an extraordinary amount of clean, whole divisions available from a single base, and it made the system remarkably practical for exactly the kind of fraction-based accounting that trade and taxation and the careful sharing out of grain and goods actually required, day after day, in a working economy. And here's the part worth letting settle quietly in your mind tonight, since you are in fact still living inside this ancient system, right now, without ever having chosen to. 60 seconds make a minute, 60 minutes make an hour, 360 degrees make a full circle. Every one of those numbers traces directly back to Sumerian and Babylonian mathematics, worked out in that river valley roughly 4,000 years ago, long before almost anything else you might associate with the ancient world had even come into being. Every single time you glance at a clock, you are, in a small and quiet way, still counting the way the Sumerians once counted, still living inside a system built to solve a problem about grain and wages and temple offerings so many thousands of years ago. The Babylonians, who came after the Sumerians and carried this mathematics forward, added one more genuinely important refinement, something worth pausing on for a moment. They developed what's called a place value system, meaning the position of a symbol within a number changed its meaning, not just the symbol's shape alone. This is exactly the same idea, sitting quietly inside our own numbers today. The digit 5 means something different, depending on where it sits. In the number 50, it means 5 groups of 10. In the number 500, that very same digit means something 10 times larger again, purely because of its position within the whole number. The Babylonians had worked out a version of this same insight almost 2,000 years before it would eventually reappear in India, in the form that would one day become the numerals you write every single day of your life. Their system wasn't quite complete, though, and the gap left behind by what was missing turned out to matter a great deal. For a long stretch of Babylonian history, there was no symbol at all for 0, no simple, clean way to mark an empty position within a number. This meant that context alone had to carry the weight of telling a reader what a symbol actually meant, whether it stood for 1, or for 60, or for 3,600. Picture, for a moment, writing out a whole sentence with no spaces at all between the words, leaving the reader to work out, on their own, where one word ends and the next one begins. That is roughly what reading Babylonian numbers required, for a very long time, workable enough to get by, but genuinely, quietly ambiguous, in a way that would eventually need solving, by someone else, somewhere else, centuries later. Let this settle for now, gently, without needing to hold on to any particular date or detail. What matters most here is the shape of the story. A civilization built cities and grain stores and temples and trade routes, and in doing so, ran directly into a problem that simple tally marks could never solve. And out of that problem, slowly, patiently, over centuries, came clay tokens, and then impressions in wet clay, and then written symbols standing entirely on their own, and then a whole system of counting in groups of 60, still quietly ticking away on every clock in every room, including, most likely, somewhere near you right now, in the dark, as you rest. Let's settle back into the story for a moment, gently, right where we left off. We were sitting with the Babylonians, and their strange, quiet gap, the missing symbol for empty space inside a number, a small flaw, sitting inside an otherwise remarkable system. Let that thought rest for now, because there's something else the Babylonians left behind that deserves a few minutes of your attention tonight, something that shows just how far their thinking had already traveled, long before anyone in Greece had written a single word about triangles. There is a particular clay tablet, small enough to fit easily in one hand, that scholars today call Plimpton 322, named simply after the collector who once owned it. It was made somewhere around 1800 BCE, which means it is older than almost anything you would normally associate with ancient mathematics, older by well over 1,000 years than the Greek thinkers most people picture when they hear the word geometry. On its surface are 15 careful rows of numbers, arranged in neat columns, and for a long time nobody quite knew what to make of them. But when modern scholars sat down and worked through what those numbers actually meant, something quietly striking emerged. Every row describes a set of 3 whole numbers that fit together in a very particular way, the same relationship you might remember faintly from a school classroom, where 2 shorter numbers, each multiplied by itself, add up to a third number multiplied by itself. We call this the Pythagorean relationship today, named after a Greek thinker who would not be born for another 1,200 years. But here it was already, carved into wet clay, worked out by a scribe whose name we will never know, in a river valley long before Pythagoras took his first breath. This is worth sitting with quietly, because it is not simply a matter of one clever guess. The rows on this tablet are not scattered or random, they follow a clear, deliberate order, which tells us something important, that whoever produced this tablet was not stumbling onto these number sets by luck, trying combinations at random until something happened to work. They had a method, a systematic way of generating one of these number sets after another, reliably, on purpose. And yet, as far as anyone can tell, they never wrote down why the method worked, never left behind an explanation for why these particular combinations of numbers would always fit together this way, for every case, not just the 15 they happened to record. This is a distinction worth carrying with you for the rest of tonight, and we will come back to it more than once, because it sits quietly underneath almost everything that follows. There is a real difference between knowing that something works and understanding why it must always work. The Babylonian scribe who made this tablet knew that his method worked. He had tested it, refined it, trusted it enough to carve it permanently into clay. But knowing a pattern holds, even knowing it holds again and again, is not the same as proving that it can never fail, that no exception could ever quietly be waiting somewhere further down the list. That second kind of certainty, the kind built entirely from pure reasoning rather than repeated observation, was still centuries away, waiting patiently in a part of the world that had not yet begun asking that particular question. While all of this was happening in Mesopotamia, a separate and largely independent mathematical tradition was quietly taking shape a little further west, along the banks of a different river entirely, the Nile, in what we now call Egypt. And this tradition, in its own way, grew out of a problem every bit as pressing as the one that had pushed the Sumerians toward their clay tokens and tablets, a problem tied directly to the land itself and to water. Every year, without fail, the Nile flooded. Around the same time each season, the river rose, spread out across its banks, and covered the surrounding fields in a slow, steady layer of water. When the water finally receded, weeks later, it left the land richer, softer, ready for planting, but it also left something else behind, a kind of quiet chaos. The boundaries between one farmer's field and the next, the careful lines that had marked out who owned what, were gone, washed away, blurred beneath the mud. And so, every single year, officials had to walk back out onto that muddy, reshaped land and figure it all out again, remeasuring where each field began and ended, so that taxes could be calculated fairly, so that ownership could be settled without endless dispute. This is, quite literally, where a word you already know came from. The word geometry is built from two old Greek pieces, one meaning earth and one meaning to measure. Earth measurement. And while the Greeks are the ones who eventually gave this discipline its name, centuries later, it was the Egyptians who were actually doing this work first, out in the mud, year after year, long before anyone in Greece had thought to name it anything at all. Egyptian surveyors used long ropes, knotted at careful, even intervals, stretching them tight across the fields to measure distance, to mark straight lines, to lay out right angles where they were needed. A rope with knots might seem like a small, humble tool, almost too simple to matter, but in the right hands, stretched carefully across a muddy field beside the Nile, it became the very beginning of geometry as a working, practical craft, born not from abstract curiosity, but from mud and boundaries and the quiet, yearly need to know exactly where one person's land ended and another's began. We actually know a fair amount about how these Egyptian mathematicians thought and worked, because of a document that has survived, remarkably, across nearly 4,000 years. It is called the Rhind Mathematical Papyrus, named after the collector who acquired it in the 19th century, though it was originally copied out by a scribe named Ahmes, sometime around 1650 BCE. Ahmes tells us, in his own opening words, that the material he is copying is even older still, drawn from knowledge that had already been passed down for generations before his own hand ever touched the papyrus. What survives is something like a practical mathematics textbook, a working manual rather than a grand theoretical treatise. It contains 87 separate problems, and they are wonderfully ordinary in what they ask, calculating how much grain is needed to feed a certain number of animals, figuring out how to divide loaves of bread fairly among a group of workers, working out the area of a field, or the volume of a granary. This was mathematics built to solve the actual everyday problems of running a household, a farm, an entire kingdom, not mathematics built to explore abstract questions for their own sake. One small detail about how the Egyptians handled fractions is worth mentioning here, gently, because it shows just how differently two civilizations can approach the very same idea. With one single exception, the fraction we would call 2/3, every other fraction the Egyptians used had to be written as a sum of separate fractions, each one with exactly one on top. So instead of writing something we might casually think of as 3/4, an Egyptian scribe would need to express that same quantity as 1/2 plus 1/4, added together. It sounds cumbersome to modern ears, and in many ways it genuinely was, making certain calculations more complicated than they strictly needed to be. But it worked, consistently, reliably, for thousands of years of Egyptian trade, taxation, and daily life, which is really all any working mathematical system ever needs to do. And the Egyptians did not stop at fields and grain stores. They turned this same careful, practical mathematics towards something far larger, something you have probably seen a photograph of at some point in your life, even if you have never stood in front of it yourself: the pyramids. The Great Pyramid of Giza, built for the pharaoh Khufu around 2560 BCE, required a level of mathematical precision that is still, honestly, a little difficult to fully picture. Its base is almost a perfect square, and the four sides differ from one another by only a matter of centimeters, spread out across a length of more than 230 meters. Its faces line up closely with true north, south, east, and west, not roughly, but closely, in a way that could not possibly have happened by accident or rough guesswork. None of that precision came from luck. It required a real, working understanding of right angles, of ratios, of how to take a plan that exists only on a small scale, in someone's mind or on a piece of papyrus, and project it accurately across a vast patch of desert, holding that same precision steady across years of construction, coordinated among tens of thousands of workers who each needed to understand, in their own small piece of the project, exactly where their work fit into the larger whole. We do not have a surviving document that explains, step by step, exactly how the Egyptians managed this, which means that some part of this achievement remains, even now, a quiet, unanswered question, sitting patiently in the sand, the way it has for well over 4,000 years. So by this point in the story, two separate river-valley civilizations, each shaped by its own particular river, each solving its own particular problems, had independently built remarkably sophisticated mathematics. The Babylonians had their base 60 numbers, their careful place value system, and, as that tablet shows us, a working understanding of number relationships that would not be formally explained for another 1,000 years. The Egyptians had their rope-stretched geometry, their practical fractions, their pyramids standing as proof that careful measurement, applied patiently and consistently, could raise something enormous and lasting out of nothing but sand and stone. And yet, in both places, something was still quietly missing, a question that had not yet been asked, or at least not yet answered in any way that survived. Both civilizations knew, with real confidence, that their methods worked. They had tested them, refined them, trusted them across generations. But neither one had yet asked why, in the deeper sense, why a particular method for measuring a field would always give the correct area, no matter how the field was shaped, why a particular relationship between the sides of a triangle would hold true in every single case, including ones nobody had ever actually measured. That question, quiet and patient, was still waiting, resting somewhere across the water, in a part of the world just beginning, slowly, to trade with both of these old river valleys, carrying their numbers and their methods toward a place that would eventually ask that very question, and change, quietly and permanently, what mathematics was even for. Let's pick the thread back up gently, right where we left it last time, with those two river valley civilizations, Mesopotamia and Egypt, each having built something quietly remarkable in its own way, each having found methods that worked, reliably, year after year, generation after generation. But there was still something missing from both of them, a particular kind of question that neither civilization had quite gotten around to asking. And tonight we're going to sit with the moment that question finally arrived. It arrived by way of trade, the way so many ideas travel, carried not by armies or conquest, but by merchants and sailors moving goods back and forth across open water. Somewhere around the 6th century before the Common Era, Greek traders and travelers began encountering both of these older mathematical traditions, the Babylonian and the Egyptian, more and more directly, picking up their methods the way you might pick up a useful tool from a neighboring workshop. The Greeks inherited a great deal from this contact. They inherited ways of calculating area, ways of handling fractions, ways of tracking the movement of stars precisely enough to build working calendars. This was, in its own right, an enormous inheritance, centuries of hard-won practical knowledge, handed across the water almost for free. But here is the part worth sitting with quietly for a moment, because it is the hinge on which this entire evening's story turns. The Greeks inherited the methods, but they did not inherit any explanation for why those methods worked. A Babylonian scribe could tell you, with real confidence, that a certain technique for measuring a field would give you the correct area, because it always had, every single time it had been tried. But nobody, as far as we can tell, had ever stopped to ask whether it would always work, in every possible case, including cases nobody had happened to try yet. This might sound like a small, almost pedantic distinction, the kind of thing that hardly seems worth mentioning. But it is not small at all. It is, in fact, the exact seed from which everything we now recognize as mathematics eventually grew. The man most often credited with planting that seed is Thales, who lived in a Greek city called Miletus, on the coast of what is now Turkey, sometime around 624 to 546 BCE. We do not know a great deal about Thales with any real certainty. None of his own writing survives, and everything we know about him comes second-hand, through later writers describing a man they themselves had never met. But the tradition that grew up around him credits him with something genuinely new, being the first person to prove mathematical statements through logical reasoning, rather than simply asserting them because they had always seemed true, or because a trusted elder had said so. There is a story about Thales, likely softened and reshaped by centuries of retelling, that captures something true about what he represented, even if the details are not perfectly accurate. It says that Thales calculated the height of the Great Pyramid without ever climbing it, without measuring it directly at all. Instead, he waited until the moment his own shadow, cast by the sun, was exactly as long as he himself was tall. At that precise moment, he reasoned, the pyramid's shadow must also be exactly as long as the pyramid itself was tall, since the same sun was casting both shadows at the same angle. So he simply measured the shadow, lying flat and easy to measure on the ground, and in doing so he knew the height of a structure far too large and far too dangerous to measure directly. Whether or not this exact story happened precisely as described, it captures the heart of what made Thales different. He trusted reasoning itself, logic and ratio working together, to reach a certain answer, rather than needing to physically touch or climb the thing he wanted to understand. This new way of thinking, that a person could reach certainty through pure reasoning, rather than through direct observation alone, needed a problem substantial enough to really test it, and that problem arrived through a man named Pythagoras, born around 570 BCE on the island of Samos. Pythagoras eventually settled in southern Italy, where he founded a community that was, by all accounts, an unusual blend of things, part school, part religious order, part tightly guarded secret society. The people who gathered around him believed something quite striking, that numbers were not simply useful tools for counting sheep or measuring grain, but the actual underlying substance of reality itself. To the Pythagoreans, the movement of the stars, the sound of music, even the human soul, could all, in some deep sense, be understood as relationships between whole numbers. You may already know the relationship most closely tied to this man's name, even if you have not thought about it in years. If you have a triangle with one perfectly square corner, what we call a right angle, then something quietly elegant is always true about its three sides. Take the two shorter sides, multiply each one by itself, and add those two results together. That sum will always equal what you get when you multiply the longest side, the one stretching opposite that square corner, by itself. This holds true every single time, for every right triangle that has ever existed or ever will. Now, it's worth remembering something from earlier tonight, that this same relationship was already sitting quietly on that Babylonian tablet we discussed, carved into clay over 1,000 years before Pythagoras was even born. What Pythagoras and his followers actually contributed was not the discovery of the relationship itself, but something rarer, a genuine logical proof, a chain of reasoning showing that this relationship had to hold true for every possible right triangle, everywhere, always, not merely the particular ones anyone had happened to measure by hand. And it was inside this very achievement, their proudest and most defining discovery, that something deeply unsettling was quietly waiting to be found. Picture a right triangle where both of the two shorter sides measure exactly 1 unit in length, nothing complicated, just 1 and 1. According to their own theorem, the longest side of this triangle must have a length equal to some number which, multiplied by itself, gives exactly 2. So the Pythagoreans went looking for that number, trusting, as they always had, that it would turn out to be some clean ratio of whole numbers, since that was the only kind of number their entire worldview allowed for. And they found something troubling. You can get closer and closer to the right answer, 1 and 4/10, 1 and 41/100, refining the guess again and again. But you can never land on it exactly, not through any ratio of two whole numbers, no matter how patiently you search. A member of their own circle, likely a man named Hippasus, is credited with proving that this particular number, what we would now call the square root of 2, simply cannot be written as a ratio of whole numbers at all. It was, in the strict sense of that word, irrational, not foolish or unreasonable, but literally without a ratio. For a group of people whose entire understanding of the universe rested on the belief that whole numbers and their ratios were the fundamental fabric of everything, this was not a minor inconvenience to quietly set aside. It was closer to watching the floor give way beneath a house you had trusted completely. According to legend, more myth than verified history, but revealing all the same in what it suggests about how seriously this was taken, Hippasus was thrown overboard from a ship by his own fellow Pythagoreans, drowned for having revealed a truth that threatened to unravel everything they believed. Whether or not that particular story is literally true, the mathematics behind it is entirely real, and it stands as the first great crisis in the whole history of mathematics, a moment when careful, honest reasoning produced an answer nobody wanted, an answer that broke apart an entire picture of the world and forced it to be rebuilt on steadier ground. This is worth letting settle quietly here in the dark, because it says something true about how mathematics actually grows, something that runs against how most of us instinctively picture it. It does not grow through calm, comfortable accumulation, each generation simply adding a little more to an ever-expanding, orderly pile of facts. It grows, instead, through exactly this kind of moment, when a rigorous method leads somewhere nobody wanted to go, and the only honest choice is to follow the logic anyway, and rebuild whatever needs rebuilding around what turns out to be true. The discovery of irrational numbers did not destroy mathematics. It revealed, quietly and permanently, that the world of numbers was stranger and larger than anyone had assumed, and that the whole numbers people had been counting with for tens of thousands of years were only a small, orderly corner of something far bigger. Before we move toward the framework that this crisis would eventually help bring about, it's worth resting for a few minutes on one more figure from this same broad stretch of history, because his work shows just how far pure reasoning could reach, even without any of the instruments we take for granted today. Eratosthenes of Cyrene worked as the head librarian of the Great Library of Alexandria around 240 BCE, and he wanted to know something that must have seemed almost impossible to determine: the actual physical size of the Earth itself, a planet no person in his lifetime could ever hope to circle or view from above. He had heard something curious about a town called Syene, far to the south. There, at exactly noon on the summer solstice, sunlight fell straight down a deep well without casting any shadow at all, meaning the sun sat directly overhead at that precise moment. On that same day, at that same hour, in Alexandria, Eratosthenes measured the shadow cast by a simple vertical stick and found that the sun there was not directly overhead, but tilted slightly off to one side, by an angle he could measure with real precision. Knowing roughly how far apart the two cities were, and reasoning that this small difference in shadow angle must correspond, in some proportional way, to the actual curve of the Earth's surface across that same distance, Eratosthenes used simple geometric ratios, the same basic kind of reasoning Thales had once used with the pyramid and its shadow, to calculate the circumference of the entire planet. His result, accounting for some uncertainty about the precise units he used and the exact distance between the two towns, came out remarkably close to the true value, achieved with nothing more than a well, a stick, careful observation, and patient reasoning, roughly 17 centuries before anyone would sail around the world to confirm the answer directly, with their own eyes, on their own ship. Let this settle here for a moment before we close tonight's section. A civilization that had inherited its numbers from Babylon and its practical geometry from Egypt had begun, quietly and almost accidentally, to ask a different kind of question altogether, not simply how something works, but why it must always work, in every case, forever. That question cracked open an old and comfortable worldview, cost, according to legend, a man his life, and yet also gave a librarian in Alexandria, working with nothing but a shadow and some patient arithmetic, the tools to measure an entire planet he would never see from above. This is the shape mathematics was beginning to take, a shape built not from comfortable agreement, but from careful reasoning, followed all the way to wherever it honestly led. And it is this same shape, refined and extended, that would soon be gathered together, definition by definition, proof by proof, into the most influential mathematics book ever written. Let's settle back in, gently, right where we left off, with Eratosthenes and his well, his stick, and his careful reasoning, working out the size of an entire planet from the comfort of a library in Alexandria. That was the atmosphere Greek mathematics had built by this point in our story, a willingness to trust logic, far beyond what the eye alone could ever confirm. And it was in this same city, around this same broad stretch of time, that all of these threads finally gathered together into a single, towering achievement, one that would end up shaping how humans think about proof and certainty for the next 2,000 years. The man responsible was named Euclid, and he worked in Alexandria around 300 BCE, during the reign of a ruler called Ptolemy I, in a city that had recently become one of the great centers of learning in the ancient world. It is worth pausing, gently, on how little we actually know about Euclid the person. We have no confirmed birthplace for him, no confirmed dates of birth or death, almost nothing about his daily life, his personality, his friendships, the small, ordinary details that usually survive about a person, even from so long ago. What survives instead is simply his work, a 13-book collection called The Elements, and this single text may be the most influential mathematics book ever written in the whole of human history. For roughly 2,000 years, right up until well into the 20th century, students learning geometry in schools scattered across the entire world were, in one translated form or another, still reading Euclid's own words. Let's slow down here, because understanding what Euclid actually did is worth taking some real time over, since it is the single idea that separates mathematics, as you understand it today, from almost every other kind of knowledge a person can hold. Euclid did not simply gather up known geometric facts and record them the way a reference book might, the way that old Egyptian papyrus we talked about earlier had done with its practical, everyday problems. Instead, Euclid began from somewhere much smaller and much more careful. He started with just a handful of starting points, statements so basic, so obviously true on their own, that they needed no proof at all. And then, from those few starting points alone, he built every single other geometric truth as something that followed logically, step after careful step, from what came before it. Picture it, if it helps, like building something from the ground up, brick by brick, where you refuse to ever place a new brick unless it rests firmly on bricks that are already proven solid beneath it. Euclid began with definitions, telling you precisely what a point is, a location with no size at all, what a line is, a length with no width whatsoever, what a circle is, exactly and completely. Then he laid out 5 postulates, foundational assumptions he asked the reader to simply accept without proof. Things like the idea that you can always draw a straight line connecting any 2 points, or that all right angles are, in every case, equal to one another. These 5 postulates became the foundation stones for everything else. Every theorem about triangles, every property of circles, every relationship between angles anywhere in the whole of the elements is derived step by step from just those 5 starting assumptions, using nothing but pure logic, with no appeal to measurement, no appeal to what merely looks true in a drawing, nothing at all but careful deduction. This method has a name, the axiomatic method, and it stands as one of the most powerful ideas human beings have ever developed, in any field, at any point in our whole shared history. Once you accept those 5 postulates, you are, in a real sense, logically compelled to accept every single theorem that follows from them. Whether or not the conclusion feels intuitive to you, whether or not you particularly like where the reasoning happens to lead. Proof, understood this way, is not persuasion. It is not simply making an argument that sounds convincing enough to win someone over. It is a chain of logical steps where each individual link follows with total certainty from the one just before it, all the way back down to those 5 original starting assumptions. If you accept the foundation, you have no honest choice left but to accept everything that has been carefully built on top of it. Let's walk through what this actually looks like in practice, slowly, because understanding just one of Euclid's own proofs will help everything else settle more easily into place. Consider one of the earliest and most elegant results found in the Elements, the proof that the 3 angles inside any triangle always add up to exactly the same total, what we would now call 180 degrees. This holds true whether the triangle is tall and narrow or short and wide, whether it is sketched quickly on a napkin or drawn out at the scale of an entire continent. Euclid did not prove this by drawing out 1,000 different triangles and measuring their angles with increasing care, hoping the pattern would simply hold. Measurement, no matter how patient or precise, could never prove that something holds true for every possible triangle, including the countless ones nobody has ever actually drawn. Instead, Euclid used a method involving a single line, drawn through one corner of the triangle, running parallel to the side directly opposite it. Using an earlier fact he had already proven, that when a line crosses 2 parallel lines, certain pairs of angles it creates turn out to be equal to one another, he was able to show that the 3 angles of the triangle, when rearranged along that parallel line, fill it completely, forming one continuous straight line. And a straight line, by definition, always measures exactly 180 degrees. Therefore, the 3 angles of any triangle must always sum to that same value, every single time, for every triangle that has ever existed or ever will. Not because anyone measured every possible triangle by hand, but because it follows with total logical necessity from definitions and postulates laid out many careful pages earlier. This is worth holding on to gently as we move forward tonight. So let me say the same idea once more, in slightly different words, because it genuinely matters enough to repeat. From this point forward in our story, mathematics stops being primarily about noticing useful patterns through simple observation and becomes primarily about establishing certain truths through unbreakable logical necessity. A pattern noticed out in the world might hold true 99 times in a row, and then quietly fail on the 100th. A proof, properly and carefully constructed, cannot ever fail, because it does not depend on the world cooperating with it in any way. It depends only on logic itself holding together, which, as far as anyone has ever found, it always does. The Elements is organized with a remarkable amount of care. The first 6 books cover what we call plane geometry, the geometry of flat shapes, lines, triangles, circles, and the many relationships between them, eventually including a full, rigorous proof of the Pythagorean theorem, built entirely from the ground up, using only Euclid's own definitions and postulates, rather than relying on the earlier, less formally justified version the Pythagoreans themselves had worked with. Books 7 through 9 turn instead to number theory, the properties of whole numbers themselves, and it is here that we find a proof that there are infinitely many prime numbers, those numbers greater than 1, that can only be evenly divided by themselves and by 1. This particular proof deserves a few quiet minutes of your attention tonight, because it is short, genuinely ancient, and still considered, even now, one of the most beautiful arguments in the entire history of mathematics. Euclid wanted to show that no matter how many prime numbers you have already found, there is always at least one more waiting somewhere beyond them, that the primes simply never run out. His method was to imagine, just for the sake of argument, that they did run out somewhere, that there existed some final, largest prime number, and that you had in your hands a complete list of every prime number that would ever exist. He then asked you to multiply every single prime number on that supposedly complete list together and add 1 to the result. This new number, whatever it happens to turn out to be, cannot be evenly divided by any prime number already sitting on your original list, because dividing by any one of them would always leave behind a remainder of exactly 1, since the number was specifically built to be one more than a multiple of all of them combined. But every whole number greater than 1 must be divisible by at least one prime number, since that is simply, by definition, what it means to be a whole number in the first place. So this new number must either be prime itself, or it must be divisible by some prime number that was never on your original list at all, the very list you had claimed was complete. Either way, your supposedly complete list was never actually complete. And since this same argument works no matter how long your original list happened to be, no matter how enormous the primes on it were, it proves that no finite list of primes could ever be complete. There will always be another one, waiting quietly further along. The primes simply go on forever. Notice, gently, what just happened inside that proof, because it represents a technique mathematicians still use constantly, well over 2,000 years later. Euclid did not go searching for larger and larger primes, hoping to eventually prove they never stop. Instead, he assumed the exact opposite of what he actually wanted to prove, that the primes did stop somewhere, followed that assumption carefully through pure logic until it collapsed into an impossible contradiction, and concluded, with total confidence, that the original assumption must therefore have been false all along. This method, called proof by contradiction, remains one of the single most powerful tools in all of mathematics, a way of proving something is true simply by showing, patiently and carefully, that its opposite leads logically to nonsense. The final books of the Elements, books 10 through 13, move into more advanced territory still, offering a careful, formal treatment of those same troublesome, irrational numbers that had so deeply unsettled the Pythagoreans, finally giving them a rigorous logical foundation of their own, rather than leaving them sitting uncomfortably outside the system as a kind of unwelcome exception. The work culminates in Book 13 with a full construction and proof of the 5 Platonic solids, the only 5 three-dimensional shapes in existence where every single face is an identical regular polygon, meaning every side and every angle of that polygon matches every other, and the same number of faces meet at every single corner of the shape. There are exactly 5 such shapes possible anywhere in three-dimensional space, no more and no fewer: the cube, the tetrahedron, the octahedron, the dodecahedron, and the icosahedron. And Euclid proved, using nothing whatsoever but pure logic, that these 5 are the only ones that can ever exist, that no 6th shape is hiding out there somewhere, quietly waiting to be found by someone more patient. That is a strange and quietly wonderful thing to know is settled, permanently and completely, through reasoning alone, rather than through some exhaustive search that could never fully finish. What made the Elements so extraordinarily influential, in the end, was not really the individual results contained within it, many of which, as we've already discussed tonight, were already partially known, in one scattered form or another, long before Euclid ever sat down to organize them. It was the method itself that mattered most, the axiomatic structure, starting from just a few basic, trusted truths, and building an entire, enormous, internally consistent system on top of them, through nothing but careful, patient, logical steps. This became the template, the working model, for what a rigorous mathematical proof should look like ever after, and that template would go on to quietly shape not only mathematics, but philosophy, and law, and science, for the next 2,000 years of human thought. Let that settle now, gently, here in the dark. The image of one careful, patient mind in ancient Alexandria, laying down 5 simple starting points, and building, from those alone, a structure so solid it would still be standing, essentially unchanged, 23 centuries later. Let's settle back in, gently, right where we left off, with Euclid and his 13 careful books, still standing, all these centuries later, exactly the way he built them. That structure he gave to mathematics, the axiomatic method, the idea that you start from a small set of trusted truths and build everything else on top of them through nothing but careful logical steps, did not stay locked away in Alexandria. It traveled. It got picked up by other minds, other cities, other problems. And tonight we're going to follow it to one particular mind in particular, a man who took that same rigorous, patient method Euclid had used for pure shapes and lines, and pointed it instead at the physical world itself, at water, at levers, at circles that refused to give up their secrets easily. His name was Archimedes, and he lived on the island of Sicily, in the city of Syracuse, sometime around 287 to 212 BCE. You may already know one story about him, even if you've never heard his name attached to it directly, the story of a man leaping out of a bathtub. And the story, however much it may have been polished and exaggerated over more than 2,000 years of retelling, does capture something true about how his mind actually worked. He had been asked by the king of Syracuse to figure out whether a golden crown had been secretly mixed with cheaper silver, without damaging the crown itself in the process. And the story goes that the answer came to him while he was lowering himself into a bath, watching the water rise around him, displaced by the volume of his own body. If different materials of the same weight displaced different amounts of water, then here, finally, was a way to measure purity without ever needing to melt anything down or cut anything apart. Whether or not he truly ran through the streets that day still dripping, shouting a single word of triumph, the deeper point holds up regardless. Archimedes was a man who noticed the world around him the way other people noticed abstract diagrams, who could look at something as ordinary as bathwater and see, sitting quietly inside it, a piece of mathematics nobody else had thought to pull out. This is worth sitting with for a moment, here in the dark, because it tells you something about the particular kind of mind we're talking about tonight. Where Euclid built a structure entirely from definitions and postulates, working forward through pure logic alone, Archimedes worked more like an engineer studying a machine, wanting to understand not just that something was true, but exactly how it worked, mechanically, and exactly how far it could be pushed before it broke. He was known, even by the people who lived alongside him, for becoming so consumed by a problem that he would forget to eat, forget to bathe, forget almost everything else going on around him, entirely absorbed in whatever shape or ratio was currently sitting in front of him. One of his greatest achievements, and the one worth walking through slowly tonight, involves a number you have almost certainly encountered before, without ever thinking too hard about where it actually came from. Pi. The ratio between the distance around a circle and the distance straight across it. The Egyptians and the Babylonians, centuries before Archimedes was even born, had already worked out reasonably good practical approximations of this number, good enough for building and measuring land. But a practical approximation was not what Archimedes wanted. He wanted something closer to what Euclid had wanted for triangles, a method that could tell you, with real logical certainty, exactly how close the true value had to be, no matter how far you pushed it. Here is how he did it, and it is worth picturing clearly, because the image itself is genuinely lovely. Imagine a circle. Now imagine a many-sided shape drawn just inside that circle, touching it at several points but never bulging outside its edge, and imagine another many-sided shape drawn just outside the same circle, wrapping around it snugly, never quite dipping inside. The true distance around the circle has to sit somewhere between the distance around that inner shape and the distance around that outer shape, since the circle bulges out past the inner one, but stays tucked inside the outer one. Archimedes started with a fairly simple shape for both of these, a hexagon, 6 straight sides. And then he did something quietly clever. He doubled the number of sides. 12 sides now instead of 6, fitting the circle a little more closely on both the inside and the outside, narrowing the gap between his two estimates just slightly. Then he doubled again, 24 sides, then 48, then finally 96 sides on each shape, inner and outer, wrapping the circle as closely as his patient, careful hand and mind could manage. By the time he reached those 96-sided shapes, he had squeezed the true value of pi into an extraordinarily narrow range, a range so precise that the number sitting at the center of it still matches, to several decimal places, the value scientists and engineers use today, thousands of years later, with instruments and calculating machines, Archimedes could never have imagined. And he did all of this by hand, with no decimal notation the way you would recognize it, no calculator, nothing but geometry, patience, and a willingness to keep doubling, and doubling again, however tedious that must have felt somewhere around the 40th or 50th repetition. What Archimedes was really doing here, quietly, without ever using this exact language himself, was approaching something that would not be fully named and formalized for almost 2,000 years afterward, an idea called a limit, a value that a long sequence of closer and closer approximations steadily creeps toward, getting nearer and nearer without necessarily ever needing to land on it exactly in any single step. Each time he doubled the number of sides, his estimate got a little closer to the true circle, never touching it exactly, since a circle drawn with straight-sided shapes can never become a true circle, no matter how many sides you add. But close enough, eventually, that the gap between his upper and lower estimates became so narrow it barely mattered anymore. This same idea, of getting closer and closer to something without ever quite needing to arrive, would resurface many centuries later as one of the deepest and most useful ideas in all of mathematics. For tonight, it is enough to picture it simply as narrowing a gap, over and over, patiently, the way you might narrow your eyes trying to bring something distant slowly into focus. Archimedes did not stop with circles and pi. He turned this same rigorous, patient reasoning toward the physical world in ways nobody quite had before him. He studied levers, working out precisely how a small force applied far enough from a pivot point could lift something far heavier than any person could lift with their bare hands alone, and he is remembered for a line, likely embellished with retelling but true in spirit, in which he claimed that if you gave him a place to stand far enough away and a long enough lever, he could move the entire earth itself. He studied buoyancy, that same principle about displaced water that had come to him in his bath, working it out into a full, careful, provable relationship rather than leaving it as a single clever observation. He studied centers of gravity, working out exactly where an oddly shaped object would balance perfectly on a single point, treating physical objects with the same careful logical structure Euclid had once applied only to abstract lines and circles. In doing all of this, quietly, Archimedes effectively founded an entire field that would not have a proper name for many centuries afterward, the mathematics of physical mechanics, of force and motion and balance, described not through guesswork or trial and error, but through the same kind of proof that had once been reserved only for pure, untouchable geometric shapes. Among everything Archimedes worked out across his lifetime, there was one particular discovery he considered his finest, the one he wanted remembered above all the others. He proved that if you take a sphere, a perfectly round ball, and you fit it snugly inside the smallest possible cylinder that can contain it, touching the sphere all the way around its widest point and matching its height exactly, then the volume of that sphere will always be precisely 2/3 the volume of the cylinder surrounding it. And, in a detail he found just as pleasing, the surface area of the sphere works out to exactly 2/3 the surface area of that same cylinder as well. Two different measurements, volume and surface, both landing on that same clean, simple ratio, sphere to cylinder. He found this relationship so satisfying, so representative of everything his life's work had been reaching toward, that he asked, before his death, for a simple carving of a sphere fitted inside a cylinder to be placed on his tombstone, so that anyone who ever came looking would know, at a glance, what had mattered most to him. Archimedes died in 212 BCE, during a Roman siege of his home city of Syracuse. The story that has come down through the centuries, likely simplified in the retelling but again true in its essence, describes him sitting outside during the chaos of the invasion, entirely absorbed in a geometric diagram he had drawn in the sand, working through some problem that mattered more to him, in that moment, than the soldiers moving through his city. A Roman soldier approached him, and Archimedes, according to the tradition, asked only that his circles not be disturbed. It did not go the way he hoped. More than a century later, the Roman writer and statesman Cicero, traveling through Sicily, went looking for the grave of a mathematician most people around him had already stopped thinking about. He found it overgrown, tangled in brush, nearly forgotten, and he recognized it, in the end, by exactly the marker Archimedes himself had requested, that small carved image of a sphere resting inside a cylinder, still visible beneath the weeds. He had it cleared and restored, a small, quiet gesture connecting a man's proudest mathematical discovery directly to the stone marking where his body had come to rest. Let this settle for a moment, here in the dark, before we move forward into what came next. Euclid gave mathematics its skeleton, its careful logical bones, built from definitions and postulates and unbroken chains of proof. Archimedes took that same skeleton and gave it muscle, pointing it outward at circles, at levers, at floating bodies, at the physical shape of the world itself, and showing, again and again, patiently, one doubled polygon at a time, that the same certainty Euclid had found in triangles could reach just as far into water, into stone, into the ordinary physical stuff surrounding an ordinary life. Rest here for a moment. There is more of this thread still waiting, further along, whenever you're ready for it. Let's settle back in, gently, right where we left off, with Archimedes and his tombstone, that small carved sphere resting inside its cylinder, marking the grave of a man who spent his life finding the exact, provable relationships hiding inside ordinary shapes. Greek mathematics did not stop with him. It kept moving forward, kept finding new territory to explore, carried by other minds who took the same patient, rigorous approach and pointed it in directions nobody had thought to look before. Not long after Archimedes, another Greek mathematician named Apollonius of Perga, working around 200 BCE, turned his attention to a family of curved shapes that come from a surprisingly simple starting point, a cone. Picture an ordinary cone, the kind of shape you might picture if you imagine a party hat, or a certain kind of lampshade, tapering from a wide circular base up to a single point. Now imagine slicing through that cone with a flat plane, at different angles. Slice straight across, parallel to the base, and you get a circle. Tilt that slice just slightly, and the circle stretches into an oval shape, what mathematicians call an ellipse. Tilt it further, at just the right angle, matching the slope of the cone's own side, and you get a curve that opens outward forever, never closing, called a parabola. And if you slice through a double cone, two cones joined at their points like an hourglass, at a steep enough angle, you get two separate curves, mirroring each other, called a hyperbola. Circle, ellipse, parabola, hyperbola. 4 different shapes, all coming from the same simple cone, depending only on the angle of the cut. Apollonius wrote an extensive treatise working through the properties of these curves with tremendous care, using the same kind of rigorous logical proof Euclid had used for triangles and circles. And here is the quiet, remarkable part of this story, the part worth sitting with for a moment tonight. Apollonius had no practical reason for any of this. He was not trying to solve an engineering problem, or measure a field, or calculate a tax. He was simply curious about what happens when you slice a cone at different angles, and he followed that curiosity all the way through, page after careful page, purely because the logic itself was interesting to him. Nearly 2,000 years later, those same 4 curves turned out to be exactly the shapes that describe the actual paths of objects moving through space. A planet orbiting the sun traces out an ellipse. A ball thrown through the air traces out a parabola. A comet passing through the solar system just once, never to return, traces out a hyperbola. When Johannes Kepler and later Isaac Newton worked out the mathematics of orbits and motion, centuries after Apollonius had died, they reached directly for his work on conic sections, because it was already sitting there, complete and rigorously proven, waiting for a use nobody could have possibly imagined when it was first written down. Apollonius was mapping out mathematical territory that physics itself would not need for almost 2,000 years. This is worth pausing on, because it is a pattern that repeats again and again throughout the story we are walking through tonight, and it will repeat again before we are finished. Mathematics developed for no practical reason at all, purely out of curiosity. purely because a particular question felt interesting to whoever was asking it, has a strange tendency to become exactly the tool some much later scientist or engineer needs, sometimes centuries after the original mathematician is gone, with absolutely no way of ever knowing their quiet, careful work would eventually matter to anyone at all. Let that settle for a moment. A man tracing curves on a cone, for the simple pleasure of understanding them fully, ends up handing the future exactly what it will need to describe the motion of worlds. A little later still, another mathematician working in Alexandria, a man named Diophantus, took Greek mathematics in yet another direction. He worked sometime around 250 CE, several centuries after Euclid and Archimedes, and his interests were different from theirs in a meaningful way. Where Euclid had been building a grand, unified logical structure, one proof resting on the last, and Archimedes had been pointing rigorous logic at physical objects like levers and spheres, Diophantus turned his attention to something narrower and, in its own way, more puzzle-like. He was interested in equations, specifically in finding whole number or simple fraction solutions to particular kinds of algebraic problems, questions where you are given some relationship between unknown quantities and asked to find numbers that satisfy it exactly. His collected work, gathered into a text called the Arithmetica, reads differently from the Elements. It does not try to build one grand, interconnected system from a handful of starting assumptions. Instead, it moves from puzzle to puzzle, working out clever techniques for solving one kind of numerical problem after another. This might sound like a smaller achievement, somehow, compared to what Euclid or Archimedes accomplished, but it represents something genuinely important all on its own, an early and serious step toward what we would later come to call algebra, the branch of mathematics concerned with unknown quantities and the rules for working with them. Diophantus's name survives today, still actively used, in the term Diophantine equations, a phrase mathematicians still use for exactly the kind of whole number puzzle he spent his life working through, and these remain, even now, an active area of genuine mathematical research, questions people are still working to answer. So by this point in our story, Greek mathematics had, across several centuries and several very different minds, built something remarkable. Euclid had given it an unshakable logical foundation, the axiomatic method, definitions and postulates and careful proof, one step following necessarily from the last. Archimedes had shown that this same rigorous approach could reach out into the physical world, into circles and levers and floating bodies, and still hold on to its certainty. Apollonius had shown that pure curiosity, followed carefully and patiently, could map out territory that would not find its true purpose for almost 2,000 years. And Diophantus had begun nudging mathematics toward the world of equations and unknowns, a thread that other mathematicians in other places would eventually pick back up and carry much further. But something else was happening at roughly this same broad stretch of time, far to the east, in a tradition that had developed largely on its own, with little direct contact with the Greek world for much of its history. In India, mathematicians had been working with sophisticated numerical systems for a long while already, quietly developing ideas that would, in time, turn out to matter as much to the future of mathematics as anything the Greeks had built. And the breakthrough that changed everything, the one worth sitting with carefully here in the dark tonight, came into full clarity through the work of a mathematician and astronomer named Brahmagupta, working around 628 CE. Brahmagupta did something that sounds, on the surface, almost too simple to matter. He took the idea of zero, an idea earlier civilizations, including the Babylonians we talked about earlier, had used only as a kind of placeholder, a way of marking an empty position in a number, so a reader would not confuse one number for another, and he turned it into something else entirely. He treated zero as a real number in its own right, not an absence, not a gap, an actual quantity you could add, subtract, and multiply, following clear, consistent rules, the same way you might work with any other number. He wrote down, carefully, that a number added to zero stays exactly the same number, unchanged, that a number multiplied by zero collapses down to zero itself, no matter how large the original number was. And he even attempted, with less success, since this particular question turns out to be genuinely strange, to work out what happens when you try to divide a number by zero, a puzzle so slippery that mathematicians would keep refining and correcting the answer for centuries after Brahmagupta first wrestled with it. It is easy to let this slide past without noticing how significant it actually was, so let's slow down and say it again, a little differently. For a very long time, zero had been treated as a kind of absence, a way of saying nothing is here, a gap you needed to mark, so the rest of a number made sense. Brahmagupta gave that absence a full, working identity. He made nothing into something, mathematically speaking, a number that behaved according to its own rules, sitting comfortably alongside 1, 2, 3, and every other number you might name. Combined with a place value system, the same basic insight the Babylonians had partly worked out almost 2,000 years earlier, where the position of a digit determines its meaning, but now completed with a true, proper zero to mark empty positions clearly and unambiguously, India produced something you use every single day without ever thinking twice about where it came from. 9 distinct digit symbols plus a zero, arranged so that where a digit sits tells you exactly what it is worth. This is the numeral system sitting quietly behind every number you have ever written down in your life. This system did not stay confined to India. It traveled slowly westward along old trade routes, carried by merchants and scholars, into the Islamic world, where it would be preserved, refined, and eventually carried forward again into Europe, centuries later. That later journey, and the remarkable things that happened to mathematics once it reached a certain library in Baghdad, is a thread worth picking up carefully, another time, when you are ready for it. For tonight, let this settle quietly instead. A cone, sliced at different angles by a curious Greek mathematician with no practical purpose in mind at all, waiting patiently for almost 2,000 years until it became exactly what Newton needed to describe the orbit of a planet. A puzzle solver in Alexandria, working through whole number equations for their own sake, planting a small seed that would eventually grow into an entire branch of mathematics. And, quietly, patiently, somewhere else in the world entirely, a mathematician giving nothing itself a name, a value, a place at the table alongside every other number, so that one day, centuries later, you would be able to write down any quantity at all, no matter how large or how small, using nothing but 10 simple symbols and the position in which you choose to place them. Rest here for a moment. There is more of this thread still waiting, further along, whenever you are ready for it. Let's settle back in, gently, right where we left off, with Brahmagupta in India, quietly giving zero a full identity, a real place among the numbers, and that numeral system beginning its long, slow journey westward, carried by traders and travelers toward a world that badly needed it. Tonight, we follow that journey a little further, into a city that became, for several centuries, the single most important place on Earth for anyone who cared about mathematics, ideas, or the careful preservation of knowledge that might otherwise have simply vanished. That city was Baghdad, and the stretch of time we are entering now is often called the Islamic Golden Age, roughly spanning the 8th through the 14th centuries. It is worth pausing on why this period matters so much to the story we have been telling tonight, because without it, an enormous amount of what came before might never have survived to reach us at all. Think back to everything we have already walked through, the careful proofs of Euclid, the patient circle measuring of Archimedes, the abstract curves of Apollonius. All of that knowledge existed on fragile material, papyrus and parchment, copied by hand, generation after generation, vulnerable to fire, to war, to simple neglect, to the slow decay that eventually claims almost everything written down by human hands. Much of it was, at this point in history, genuinely at risk of being lost to Europe entirely, sitting in libraries that were being neglected or destroyed, in a period sometimes called the early medieval period, when much of the continent's attention had turned elsewhere, away from mathematics and toward other concerns. In Baghdad, though, something different was happening. The ruling Abbasid Caliphate supported and funded an institution called the House of Wisdom, a center of learning and translation unlike almost anything the world had seen before. Scholars there took on an enormous task, gathering Greek mathematical and scientific texts from wherever they could be found, and translating them carefully into Arabic, preserving them in a new language, on new material, copied fresh, safe for a while longer from the slow decay that had been threatening them. Euclid's Elements was translated, the works of Archimedes were translated, the treatise of Apollonius on those cone-shaped curves we talked about a little earlier was translated as well. And at the very same time, scholars in this same city were absorbing something arriving from the opposite direction, flowing in from India. That same numeral system built around Brahmagupta's zero, carried along trade routes running east to west, arriving in Baghdad and finding, quite unexpectedly, a place where people were ready to understand exactly how valuable it truly was. This is worth letting settle for a moment, here in the dark. Baghdad, in this period, sat at a genuine crossroads, a place where Greek logical rigor and Indian numerical elegance met each other for what may have been the first time, mixing together in the minds of scholars who had access to both traditions at once. It is a little like two rivers meeting, each one carrying something valuable the other did not have, joining together into something larger and more useful than either could have been completely on its own. Among all the scholars working in Baghdad during this period, one figure matters more than any other for the particular thread we are following tonight, a mathematician and astronomer named Muhammad ibn Musa al-Khwarizmi, working in the early 9th century. Al-Khwarizmi wrote a book with a long, formal Arabic title, one that translates, roughly, into something like the Compendious Book on Calculation by Completion and Balancing. Buried inside that title is a single word worth pulling out and sitting with carefully, because you have almost certainly used its descendant many times without ever thinking about where it came from. The word for completion in that Arabic title is al-jabr, and al-jabr, carried forward through centuries of translation and gradual language change, eventually became the word you already know quite well, algebra. Let's slow down here, because what al-Khwarizmi actually did in this book is worth understanding clearly, not just as a historical curiosity, but as a genuine shift in how mathematics itself worked. You may remember, from a little earlier tonight, a mathematician named Diophantus, working in Alexandria several centuries before al-Khwarizmi, who had focused on solving individual numerical puzzles, one problem at a time, each one clever in its own particular way, but without any single, unified method connecting them all together. Al-Khwarizmi did something different, something genuinely new. He worked out systematic, step-by-step procedures for solving entire categories of equations, methods that worked reliably no matter what specific numbers happened to be involved in any particular problem. He showed, for instance, general procedures for solving what we would now call quadratic equations, problems involving an unknown quantity multiplied by itself, and his methods worked the same way every single time, because they operated on the underlying structure of the equation itself, rather than depending on the particular numbers sitting inside it. Picture the difference this way if it helps. Diophantus was a bit like someone who had become genuinely skilled at solving individual locks, each one requiring its own particular trick, learned through patient trial and careful attention. Al-Khwarizmi, by contrast, was working out something closer to a master key, a single reliable method that could open an entire category of locks, regardless of their specific shape, because it worked on the shared underlying structure they all had in common. This is really the heart of what algebra is, and remains, even now, all these centuries later. Not a collection of clever individual tricks, but a general, reliable set of methods for handling unknown quantities, methods that hold true regardless of which particular numbers you eventually plug into them. Al-Khwarizmi's own name carries one more small, quiet surprise worth mentioning before we move forward tonight. Over the centuries, as his work was translated into Latin and carried further into Europe, his name itself was gradually transliterated, reshaped slightly by unfamiliar tongues and unfamiliar alphabets, the way names so often are when they travel between languages. And that gradual transformation eventually produced another word you almost certainly use, or at least encounter, constantly in your daily life, usually without ever once wondering where it came from: algorithm. Every algorithm quietly running on your phone right now, sorting through your messages, suggesting your next search, calculating your route home. Every algorithm running inside every computer you have ever touched carries, in its very name, a quiet echo of a mathematician working in Baghdad more than 1200 years ago, patiently working out step-by-step procedures for solving equations, with absolutely no way of knowing that his own name would eventually attach itself to some of the most important technology the world would ever build. Let this settle for a moment, the way we have let other things settle earlier tonight. A word for completion, algebra, becomes algebra. A scholar's own name, al-Khwarizmi, becomes algorithm. Two words you may use casually, without a second thought, both carrying, quietly, the memory of one particular mind, working carefully through mathematical problems in a city that no longer exists in quite the form it did then, more than 1,000 years ago. While all of this was happening in Baghdad, and while the threads we have already traced through Mesopotamia, Egypt, Greece, and India were weaving together in this one remarkable city, something else entirely, something largely separate and independent, was quietly developing far to the east, in China. It is worth including this thread tonight, even briefly, because it followed its own path for most of its history, with relatively little direct contact with the other traditions we have been discussing, and yet it reached, on its own, several of the same deep mathematical insights the other traditions had worked so hard to find. Chinese mathematicians had been using a counting rod system since at least the 4th century BCE. Small bamboo or bone rods arranged carefully on a flat surface to represent numbers, a physical, tactile way of working through calculations. And, notably, Chinese mathematicians worked comfortably with negative numbers many centuries before European mathematicians were willing to accept them as legitimate, treating a negative quantity not as some kind of nonsensical impossibility, but simply as a number smaller than zero, worth working with just as carefully as any other. A text called The 9 Chapters on the Mathematical Art, compiled gradually over several centuries and reaching roughly its final form around the 1st century CE, gathered together methods for land surveying, for engineering, for calculating taxes, and for solving equations, including a technique for solving several equations at once, together, as a connected system, remarkably similar to a method European mathematicians would not formally work out until the early 19th century, more than 1,000 years later, under the name of a different mathematician entirely, working in a completely different part of the world. Chinese mathematicians also arrived, entirely on their own, at early versions of that same right triangle relationship the Pythagoreans had once found so significant, along with their own increasingly refined estimates of the value of pi, including one calculation made by a mathematician named Zhu Chongzhi in the 5th century CE that remained the single most accurate estimate of pi found anywhere in the world for roughly 900 years afterward. This is worth sitting with quietly for a moment, because it says something true about mathematics as a whole, something we have circled back to more than once tonight already. Separated by enormous distances, with little or no direct communication passing between them, different groups of careful, patient people, working with whatever tools and questions happened to be available in their own particular corner of the world, kept arriving at strikingly similar truths, again and again. Not because they were copying each other, but because the truths themselves were simply there, waiting, the same way they are always waiting, for anyone patient enough and rigorous enough to go looking. So by this point in our story, tonight, mathematics had gathered together an extraordinary amount of genuine strength, though it was still, in an important sense, spread out, sitting in different places, waiting to be gathered fully into one place. It had rigorous logical proof, inherited from the Greeks. It had a flexible, complete numeral system, including a properly defined zero, inherited from India. It had a systematic, general method for handling unknown quantities, worked out carefully in Baghdad, in that word we now simply call algebra. Somewhere, quietly in China, similar insights had already been reached entirely independently, waiting for the wider world to eventually catch up. All of these pieces, still scattered, still largely separate, were slowly making their way toward Europe, carried along the same old trade routes that had carried goods, and languages and stories for centuries already, waiting for someone to gather them together in one place, and carry this whole long, patient tradition forward into what would come next. Rest here for a moment. There is more of this thread still waiting, further along, whenever you are ready for it. Let's rest here, in the quiet that settles after a long journey, with the weight of everything we have walked through together, still present, but no longer needing to be held quite so tightly. The numbers, the proofs, the centuries of patient reasoning, all of it is still here, tucked into the background of your awareness, the way a familiar sound eventually becomes part of the silence, rather than something separate from it. And now, from this place of settled attention, we can turn towards something that has been waiting quietly in the margins of this whole story, something that connects directly to where you are right now, in this room, in this dark, in this particular moment of lying still and letting your thoughts drift where they will. The thread we have followed so far, from that baboon bone in the Lebombo Mountains, through the clay tablets of Mesopotamia, the measured fields of Egypt, the logical proofs of Greece, the formalized zero of India, the algebra and algorithms of Baghdad, the calculus of Newton and Leibniz, all of it has been about something external, about describing the world outside the mind. But there is another thread, one that runs alongside this one, sometimes crossing it, sometimes diverging entirely, a thread that asks not about the world itself, but about the instrument through which we perceive the world. That instrument is the mind itself, your mind, the one that has been following along tonight, sometimes closely, sometimes loosely, sometimes drifting entirely into a space between waking and sleeping, where the words become more like texture than meaning. This section is about that space, about the borderland between waking and sleeping, and about what happens in the mind when it is no longer required to hold on to anything, when it is allowed to loosen its grip on the day's accumulated concerns and simply rest. This is not a detour from the story we have been telling. It is, in a quiet way, the place the whole story has been heading toward, because the ultimate purpose of all that mathematics, all that careful reasoning, all that accumulated knowledge, is not to fill your mind with facts to carry around. It is to give you permission to let go of the need to understand everything at once, and to trust that what matters will find its way to you, in its own time, without force. Consider for a moment what is actually happening in your brain right now as you lie there, if you have not already drifted fully into sleep. Your neurons, the cells that make up your nervous system, are communicating with each other through electrical impulses and chemical signals, each one a tiny, measurable event that could, in principle, be described using the same mathematics we have been walking through. The timing between those signals can be measured. The distances across which they travel can be estimated. The patterns of activation across different regions of your brain, as you listen to this voice and allow your thoughts to wander, could be mapped and analyzed using tools built on calculus and linear algebra and probability theory. If you were hooked up to an EEG machine, the electrodes on your scalp would pick up the rhythmic electrical activity of your brain, a pattern that changes in predictable ways as you move from full alertness toward the edge of sleep. The mathematics of wave patterns, the Fourier transform we mentioned earlier in the context of medical imaging, can be used to analyze these brainwaves, to see the frequencies that dominate at different stages of waking and sleeping, to watch, in real time, as the balance between different rhythms shifts and your consciousness gradually loosens its grip on ordinary waking awareness. But this is not the point. The point is not to analyze your brain from the outside, to treat it as a system of equations to be solved. The point is to be inside it, to feel what it is like to be a mind gently releasing its hold on the day, to notice the way a thought arises and then fades, the way an image appears in the mind's eye and then dissolves back into nothing, the way a word or a phrase from earlier tonight might surface without any apparent cause, carrying no particular meaning, just present, and then gone again. This is what your mind does, constantly, whether you are awake or asleep, generating patterns of activity that are never quite the same twice, never fully predictable, never entirely under your control. And this is where the thread of mathematics and the thread of your own inner experience come together in a way that is worth sitting with. In the early years of the 20th century, a mathematician and philosopher named Alfred North Whitehead wrote that the aim of mathematics is not just to produce correct calculations, but to produce understanding. And understanding, in this sense, is not the same as knowing facts. It is closer to a kind of spaciousness, a sense that you do not need to hold every detail in your immediate awareness, because the structure underneath those details is solid, reliable, and can be returned to whenever you need it. This is the opposite of what much of formal education assumes, that understanding means being able to reproduce information on command. Real understanding, the kind that settles into you gradually, the way sediment settles at the bottom of still water, is more like a room you know well enough to walk through in the dark, without needing to turn on a light or consult a map. You have been in that room, the room of mathematics, all night. You have walked through its corridors and paused in its quiet corners, and now, as you lie here in the dark, you do not need to keep walking. You can simply rest in the room itself, trusting that its structure will still be there tomorrow, or the day after, or whenever you might choose to return. There is a branch of psychology, developed over the past century, that has studied what happens to the mind when it is no longer required to perform tasks or solve problems, when it is allowed to simply drift. This state, often called the default mode network, involves the activation of a particular set of brain regions that become more active when you are not focused on any particular task, when your attention is not directed outward toward the world or inward toward a specific problem. In this state, your mind generates spontaneous thoughts, memories, images, fragments of language, patterns that are not under your conscious control, but that arise naturally, the way bubbles rise to the surface of still water. This is the state you are likely moving into right now, if you have not already reached it. It is the state that your mind was designed to enter regularly, for reasons that are still not fully understood, but that seem to involve consolidating memory, making connections between different experiences, and allowing your brain to rest and recover from the focused attention that fills most of your waking hours. Mathematicians and scientists more generally have often reported that their most important insights came not during periods of intense, focused work, but during periods when they had stopped working, when they were walking, or lying in bed, or doing something else entirely that did not require their full attention. This is sometimes called the incubation effect, the strange tendency of the mind to continue working on problems below the surface of conscious awareness, rearranging information, testing connections, searching for patterns, all without your active participation or even your knowledge. It is as if the mathematics itself, or the mind's own version of it, continues to run quietly in the background, the way your phone continues to run background processes even when the screen is dark and you are not actively using it. You do not need to be consciously working on a problem for your mind to be working on it. You only need to give it the raw material and then step back and trust that something will eventually emerge. This is why there is no test at the end of tonight. There is nothing to remember by force. The material has been presented, carefully, slowly, in the same way a gardener prepares soil, not by forcing seeds to grow, but by creating the conditions in which growth can happen naturally, in its own time. The seeds of tonight's story have been planted. Some of them have already found their way into the soil of your mind. Others are still drifting, settling slowly, waiting for the right conditions to take root, and the conditions for that growth, the water and warmth and stillness that allow seeds to germinate, are exactly what you are providing right now, simply by lying still, by allowing your attention to soften, by letting your thoughts drift without needing to catch them or hold them or do anything with them at all. If you find yourself returning, in the coming days or weeks, to something you heard tonight a name, an idea, a fragment of a proof. That is the growth happening. It will not happen because you forced it. It will happen because you gave it space. And the space you have given it tonight, the darkness, the quiet, the permission to let go of any requirement to remember or understand, is exactly the kind of space that allows understanding to develop naturally, without strain, without effort, without the kind of forced memorization that so often leaves nothing behind but a vague sense of having been told something important without quite knowing what it was. There is a quiet truth about human learning that is often forgotten in the noise of schedules and deadlines and the endless pressure to produce results on demand. Learning is not primarily about adding new things to your mind. It is about making space for things to settle. It is about preparing the ground, the way a farmer prepares a field, not by demanding that seeds sprout immediately, but by turning the soil, adding water, and waiting for the natural process of growth to happen on its own schedule. Tonight has been the preparation, the turning of the soil, the adding of water, the rest of it, the growth, the connections forming between what you already knew and what you have just heard. That is not something you need to manage or control. It will happen whether you direct it or not, the way your body continues to breathe, whether you think about breathing or not. As you lie there, let the boundaries soften, the boundary between what you understand and what you do not understand, the boundary between what you will remember tomorrow and what will slip away completely, the boundary between the voice you have been listening to and the quiet thoughts that are your own. These boundaries are more permeable than they often seem, more like the edges of a cloud than the walls of a room. A thought that feels like it belongs to you may have been planted by something you heard tonight, or last week, or years ago. A feeling of calm that arises without apparent cause may be the result of a realization that has not yet formed into words, but that has already begun to settle into your body, into your breathing, into the space between your thoughts. This is what the thread we have been following has been leading toward all along. Not a final conclusion, not a set of facts you can recite on demand, but a way of being in the presence of knowledge without needing to possess it. A way of allowing the vast, patient structure of mathematics to be present in the background of your awareness, the way the stars are present in the night sky, visible when you look up, but just as present when you look away, waiting patiently for you to notice them again whenever you are ready. If you have drifted, let yourself drift. If you have stayed awake, let yourself stay awake, without any requirement to make that stay useful or productive. There is nothing more to do tonight. There is nothing to solve. There is no question to answer. There is only the quiet continuation of a story that has been unfolding for tens of thousands of years, and that will continue to unfold after you have fallen asleep, and after you have woken up, and after you have gone about your day carrying with you, somewhere beneath the surface of conscious awareness, the accumulated weight of all those generations of patient thought. The room you are in will still be here in the morning. The mathematics will still be here, the same way it has been here for thousands of years, the same way it was here before anyone carved a notch into a bone, and the same way it will be here long after everyone who has ever lived is gone. It is not going anywhere. It does not need you to hold on to it. It will hold itself, the way the truth of a triangle's angles holds itself, independent of whether anyone is paying attention, independent of whether anyone understands it, independent of whether anyone even knows it exists. So rest now, really rest. Not because you have earned it, though you have, but because rest is the final and most important part of the whole process. Rest is where what has been heard becomes what is known. Rest is where the threads that have been laid down begin to weave themselves together into something that is not just information, but understanding. Rest is where you become not just someone who has been told a story, but someone who carries that story inside them, the way the earth carries the memory of every seed that has ever fallen into it. Whether that seed grew into a tree or simply returned to the soil from which it came. Let the story settle now, the way a stone settles into the bed of a river, finding the shape of the space around it without effort. And let yourself settle with it, into the darkness, into the quiet, into the simple fact of being here, in this room, at this moment, with no need to be anywhere else or anyone else, or know anything other than what you already know, which is that you are safe, and you are resting, and the rest of it can wait for another time. Whenever you are ready for more, the thread will still be here, but for now, there is nothing left to do but let go completely, the way you let go of a held breath, and trust that the story you have been carrying through tonight will find its way into the place where stories go when they are no longer being told, waiting there, quietly, until the moment comes for them to be heard again. Let's rest here for a moment longer, in the space between what has been said and what is still settling. The thread we have been following is long, and we have traveled along it together through many centuries, through many minds, through many quiet moments of insight that changed the shape of what was possible. But there is one more stretch of this thread worth walking, one that brings us closer to the present moment than any we have visited so far, and that touches on something you carry with you always, something that has been running quietly underneath everything we have discussed tonight. The branch of mathematics we are turning toward now is one that grew out of a very old question, a question that has probably occurred to you at some point, perhaps while lying in the dark, perhaps while watching something unfold in the world and wondering whether it could have happened any other way. The question is about chance, about uncertainty, about the difference between what we know and what we cannot know until it happens. And the mathematics that grew up around this question, probability, is one of the most quietly influential branches of the whole tree we have been tracing. Probability began, as we mentioned earlier, with dice and cards and the kinds of games people played when they wanted to pass the time and test their luck. The 17th century correspondence between Pascal and Fermat, working through questions about how to divide the stakes in an unfinished game of chance, laid the foundation for something that would eventually reach far beyond gambling tables. But it is worth slowing down here, because the movement from games of chance to the serious, world-changing applications of probability is one of the quietest and most consequential transitions in the whole history of mathematics. It did not happen overnight. It happened gradually, over centuries, as people began to realize that the same mathematics that could tell you the odds of rolling a certain number on a pair of dice could also tell you the odds of a particular medical treatment working, or of a bridge withstanding a certain wind, or of a financial market behaving in a certain way. At the heart of probability is a deceptively simple idea. If you have a situation where several different outcomes are possible, and you have no reason to believe that one outcome is more likely than another, you can assign equal likelihood to each possible outcome. This is the principle of indifference, and it is the starting point for most elementary probability. A fair coin has 2 equally likely outcomes. A fair die has 6. A well-shuffled deck of cards has 52, each equally likely to end up on top. From this simple starting point, you can begin to calculate the likelihood of more complex events, the chance of rolling a 7 with 2 dice, the chance of drawing 2 aces in a row, the chance of a particular hand in poker. These calculations are not guesses. They are precise, following from the same logical rigor Euclid applied to triangles. Once you accept the starting assumptions, the probabilities follow with certainty. But this is where probability begins to get genuinely interesting, and where it starts to touch something deeper than games. Because in the real world, unlike in a game with a well-defined set of equally likely outcomes, we rarely know all the possibilities, and we almost never know whether they are equally likely. A coin might be slightly weighted, a die might have a tiny imperfection, a deck of cards might not be perfectly shuffled, and even if all the physical objects are perfect, the world itself is full of uncertainties that cannot be reduced to simple counting. This is where the second great branch of probability, statistics, enters the picture. Statistics grew out of the need to make sense of data, to take a collection of observations that are noisy and incomplete and uncertain, and extract from them something that resembles knowledge. If you measure the height of 100 randomly chosen people, you will get 100 slightly different numbers. You cannot know the exact average height of the entire population without measuring everyone, which is usually impossible. But you can use statistics to estimate that average, and you can calculate how confident you should be in that estimate. This is not guesswork. It is mathematics, built on the same careful foundations as everything else we have discussed tonight. The key figure in this transition, as we noted earlier, was Carl Friedrich Gauss, working in the early 19th century. Gauss was studying the errors that crept into astronomical measurements, the small discrepancies that arose no matter how carefully you made your observations. He noticed that these errors followed a pattern, a smooth, bell-shaped curve that described how most errors were small, and larger errors became progressively rarer. This pattern, the normal distribution, turned out to be remarkably common. It appears whenever you have many small, independent factors contributing to a measurement, each one adding a tiny bit of error that is just as likely to be positive as negative. The heights of people in a large population follow this pattern. The results of repeated measurements of the same physical quantity follow this pattern. Even the small variations in the manufacturing of identical parts follow this pattern. What makes the normal distribution so powerful is not just that it describes many natural phenomena, but that it gives you a way to quantify uncertainty. If you know the average and the spread of a normal distribution, you can calculate, with mathematical precision, the probability that a new measurement will fall within a certain range. You can say, for example, that there is a roughly 95% chance that the true value you are trying to measure lies within 2 standard deviations of your estimated average. This is the language of confidence intervals, and it is the language in which most scientific results are ultimately expressed. A drug trial does not say that a treatment definitely works. It says that, based on the data, there is a certain statistical probability that the observed effect is real and not just the result of random variation. The threshold for declaring a result statistically significant, typically a probability of less than 5% that the result could have occurred by chance alone, is a convention, a human decision about how much uncertainty we are willing to tolerate before we act. But the mathematics underlying that decision, the calculation of the probability itself, is as precise as anything Euclid ever wrote down. There is another thread within probability that deserves attention here, one that connects directly to the way you make decisions in your own life, often without realizing you are doing mathematics. This is the thread of Bayesian probability, named after the 18th century English statistician Thomas Bayes. Bayes developed a way of updating your beliefs in light of new evidence, a mathematical formula that tells you how much you should change your estimate of the probability of something happening after you receive new information. The core idea is simple and deeply intuitive, even if the mathematics takes some effort to work through carefully. You start with some prior belief about how likely something is, based on what you already know. Then you observe new evidence, and you use Bayes' formula to calculate a new, updated belief, one that takes both your prior and the new evidence into account. This is not a philosophical suggestion about how people should think. It is a precise mathematical rule that tells you exactly how much weight to give to new information, given the strength of your prior belief and the reliability of the new evidence. This way of thinking has turned out to be profoundly useful across an enormous range of fields. In medicine, doctors use Bayesian reasoning to interpret the results of diagnostic tests, taking into account both the accuracy of the test and the prevalence of the condition in the population being tested. A test that is 99% accurate might still produce more false positives than true positives if the condition is very rare. In artificial intelligence, Bayesian methods are used to help machines learn from data, updating their internal models as they encounter new examples. In finance, traders use Bayesian reasoning to adjust their estimates of market risk as new economic data comes in. And in everyday life, you use something like this reasoning constantly, even if you have never heard the name Bayes. When you meet someone new, you form an initial impression based on limited information. As you spend more time with that person, you update your impression, giving more weight to the new evidence while not entirely discarding your first impression. This is Bayesian reasoning, running quietly in the background of your mind, operating according to a mathematical rule that was formalized 3 centuries ago. There is one more aspect of probability worth sitting with before we move on, because it touches on something genuinely strange and counterintuitive about how the world works. This is the law of large numbers, the mathematical principle that says that as you repeat a random process more and more times, the average of your results will tend to get closer and closer to the true expected value. If you flip a fair coin 10 times, you might get 7 heads and 3 tails, a deviation of 20% from the expected 50-50 split. If you flip it 1,000 times, the percentage of heads will almost certainly be much closer to 50%. If you flip it 1,000,000 times, it will be closer still. The law of large numbers does not say that the deviations disappear entirely. It says that they become proportionally smaller, that the random fluctuations that seem so important in small samples become negligible in large ones. This principle underlies much of what makes probability useful in the real world. It is why insurance companies can make reliable predictions about the number of claims they will receive in a given year, even though they cannot predict which specific customers will file a claim. It is why polling organizations can estimate the views of a population of millions by surveying only a few thousand carefully selected people. It is why casinos can stay in business, because the law of large numbers guarantees that over thousands of spins of the roulette wheel, the house's small advantage will play out reliably. And it is why, in the end, chance is not the same as chaos. Randomness, when viewed over enough repetitions, becomes predictable, not in its individual details, but in its overall pattern. This is one of the quietest and most reassuring discoveries in all of mathematics, that uncertainty on a small scale can become certainty on a large scale, that the same universe that seems full of random events also contains deep and reliable structures that probability can reveal. If you have ever wondered why some people seem to believe that improbable events are meaningful, that a rare coincidence must be a sign of something, the mathematics of probability offers a clear answer. Rare events are not as rare as they seem, because there are so many opportunities for them to occur. The chance that any particular person wins the lottery is vanishingly small, but the chance that someone, somewhere, wins the lottery is nearly certain, every single time the drawing is held. The chance that you personally are struck by lightning in any given year is tiny, but the chance that someone, somewhere, is struck by lightning is high enough that lightning strikes occur every day. The human mind is not naturally good at thinking in terms of probabilities. It is wired to notice patterns, to see significance in coincidences, to treat a rare event as meaningful because it feels meaningful. But probability gives us a tool for checking these intuitions, for calculating whether a coincidence is genuinely unusual or just a routine result of the sheer number of things that happen every day. This is worth holding on to, lying here in the dark, because it connects to something deeper about how we understand our own lives. We often think of the future as something that will unfold according to a plan, or at least according to a recognizable pattern. But the mathematics of probability suggests that the future is, in many ways, a matter of chance. That the exact details of what will happen tomorrow are not fixed in advance, but depend on an enormous number of small, unpredictable events. This is not a cause for anxiety, it is simply a recognition of how the world works. And the mathematics of probability gives us a way to live with that uncertainty, to make decisions that are as good as they can be given the information we have, to update our beliefs when new information arrives, and to accept that some things will always remain beyond our ability to predict with certainty. Consider, for a moment, the path of a single leaf falling from a tree. It will twist and turn in the air, carried by currents of wind that are themselves the result of temperature differences and pressure gradients and the rotation of the earth. The exact path of that leaf is, for all practical purposes, unpredictable. Too many tiny factors are at play, each one sensitive to conditions that cannot be measured precisely. But if you could watch 1,000,000 leaves fall from the same tree on 1,000,000 different days, you would see a pattern emerge. Most leaves would land somewhere near the trunk, some would land farther away, and a very few would be carried quite a distance by a particularly strong gust. This pattern, the distribution of where leaves land, is predictable, even though the path of any one leaf is not. This is the same kind of thinking that allows meteorologists to predict the weather, not with perfect accuracy, but with a known degree of confidence. It is the same kind of thinking that allows engineers to design buildings that can withstand winds of a certain strength, even though they cannot predict exactly when that wind will come, or from exactly which direction. And this brings us back to something we touched on earlier, the connection between probability and the limits of prediction. The world is full of systems that are, in principle, predictable if you know enough about their current state and the laws that govern their behavior. But in practice, we can never know enough. We can never measure the position and velocity of every air molecule in the atmosphere, or the exact temperature and pressure at every point in the ocean, or the precise state of every synapse in a human brain. And even if we could, the mathematics of chaos theory, which grew out of the work of Edward Lorenz, shows that some systems are so sensitive to their initial conditions that even the tiniest measurement error will eventually grow into a large uncertainty. This is not a failure of mathematics. It is a reflection of the fact that the universe itself has limits on how much can be known, and probability is the language we use to describe what remains unknown. If you have drifted during this explanation, that is perfectly fine. The ideas we have been walking through are not the kind that need to be held tightly. They are more like a quiet background hum, present whether you are paying attention to them or not. And the mathematics of probability is, in a way, the mathematics of that background hum, the mathematics of the quiet uncertainty that is always present in every moment, in every decision, in every breath you take. Your own body, as it lies there, is a system of immense complexity. Your heart beats, your lungs fill and empty, your neurons fire and rest, all governed by physical laws that are, in principle, describable with mathematics. But the exact timing of your next heartbeat, the exact moment when your next breath will begin, is not something that can be predicted with certainty. There is randomness in the system, small fluctuations that make precise prediction impossible. And yet your body continues to function, continues to keep you alive and comfortable and safe, because it does not need to predict the future with certainty. It only needs to respond to the present, to adjust moment by moment, to maintain the delicate balance that keeps you here, in this room, in this moment. This is a good place to pause, to let the quiet settle. The mathematics of probability tells us that we live in a world of uncertainty, but it also tells us that uncertainty can be measured and understood. It tells us that the future is not fixed, but that it is not entirely random either. It gives us a way to make decisions in the face of incomplete information, a way to update our beliefs as new evidence arrives, a way to say, with precision, how likely something is, even if we cannot say whether it will happen. And that is enough, really. It is enough to know that the world is not completely predictable, and that this is not a flaw in the world, but simply the way it is. It is enough to know that probability gives us a language for talking about that unpredictability, a language that is as precise and reliable as any other branch of mathematics. It is enough to let go of the need to know everything in advance, and to trust that the mathematics of uncertainty will be there when you need it, quietly running in the background, the way it has been running for centuries. Rest now, if you have not already. The thread we have been following will still be here when you come back to it. The same way the numbers themselves will still be counting. The same way the probabilities will still be waiting to be calculated. The same way the quiet uncertainty of the world will continue to unfold, moment by moment, without needing anyone to fully understand it. Let the mathematics of chance settle into the background of your awareness, the way the hum of a distant fan settles into the background of a quiet room, present but no longer needing attention. There is nothing more to hold on to tonight. There is only this moment, and the next, and the one after that, each one carrying its own small measure of uncertainty, each one unfolding exactly as it is meant to unfold. Let's rest here for a moment, in the quiet that follows a long journey, with the full weight of what we have walked through together, settling into the background of your awareness. We have traveled from a bone with notches carved into it in a cave in southern Africa, through the clay tablets of Mesopotamia, the measured fields of Egypt, the logical proofs of Greece, the formalized zero of India, the algebra and algorithms of Baghdad, the calculus of Newton and Leibniz, the probability and statistics that grew from games of chance, and the strange, abstract branches that opened up in the 19th and 20th centuries. Each step along this thread was tied by a real person, working with the tools and questions available in their own particular moment, unable to see very far ahead, unable to know which parts of their work would matter and which would be forgotten. And now, as we approach the end of this telling, there is one more thread to follow, one that brings us closer to the present moment than any we have visited so far, and that touches on something you carry with you always. This is the thread of how mathematics became woven into the ordinary fabric of everyday life, how it moved from the minds of scholars working in isolation to the quiet infrastructure that surrounds you right now, in this room, in this dark, in this particular moment of lying still and letting your thoughts drift. The transition we are tracing now is not a single event, not a single breakthrough or a single name. It is a slow, gradual process, one that took centuries, and that is still unfolding. It is the process by which mathematics left the page and entered the world, by which the abstract structures that Euclid and Archimedes and Al-Khwarizmi and Newton and Leibniz built became the invisible machinery that runs underneath almost everything you touch, everything you see, everything you rely on, without ever thinking about it. Consider for a moment the room you are in. It has walls, a floor, a ceiling. The walls are straight, the corners are right angles, the floor is level. None of this happened by accident. It was built according to plans, and those plans were based on geometry, on the same principles Euclid formalized over 2,000 years ago. The builders who put up those walls may never have read Euclid, they may not have known his name, but they were using his geometry, the same way you use language, without knowing the history of every word you speak, the right angles, the level surfaces, the straight lines. All of them trace back to the same logical structure that Euclid built, one definition and one proof at a time. The light that might be glowing somewhere in your room, a charging cable, a hallway nightlight, depends on mathematics as well. The electricity that powers it was generated somewhere, transmitted across distances, transformed in voltage, delivered to your home, and distributed through the wiring in your walls. Every step of that process was designed using mathematics, using the same calculus that Newton and Leibniz developed, using the same complex numbers that Cardano first encountered as a strange intermediate step in solving cubic equations, using the same electromagnetic theory that James Clerk Maxwell formulated in the 19th century, a theory that was itself built on the same differential equations that grew out of calculus. The electricity itself, the alternating current that flows through the wires, oscillates back and forth many times each second, a rhythm that can be described precisely using trigonometric functions, the same sine waves that mathematicians had been studying for centuries as purely abstract curves, with no idea that they would one day describe the flow of power through the electrical grid. If you have ever used your phone to find your way somewhere, you are relying on mathematics that spans thousands of years and multiple civilizations. The geometry that Euclid formalized is used to calculate your position from the signals of satellites. The calculus that Newton and Leibniz developed is used to correct for the motion of those satellites and the curvature of their orbits. The non-Euclidean geometry that Lobachevsky and Bolyai developed in the 19th century is used to correct for the effects of general relativity, because time passes at a slightly different rate on a satellite than it does on the surface of the Earth. The probability theory that Pascal and Fermat worked out in the 17th century is used to estimate the uncertainty in your position, to give you a circle on the map that represents where you might be, not where you definitely are. Every time you check your location, every time you follow a route, every time you arrive somewhere you have never been before, you are relying on mathematics that was developed for reasons that had nothing to do with navigation, by people who could not have imagined the world you live in. Your phone itself, the device you may have used earlier today, and that may be resting somewhere near you right now, is a physical realization of ideas that were purely abstract when they were first developed. The transistors inside it operate according to the principles of quantum mechanics, and quantum mechanics is built on mathematics that was developed in the early 20th century, on the same linear algebra that mathematicians had been studying for generations as a branch of abstract algebra, with no idea that it would one day describe the behavior of subatomic particles. The algorithms that run on your phone, the ones that sort your messages and suggest your next search and calculate your route home, trace their name back to al-Khwarizmi, working in Baghdad over 1,200 years ago, formalizing step-by-step procedures for solving equations, with no way of knowing that his name would eventually attach itself to the most important technology the world would ever build. The music you might have listened to earlier today, or that might be playing quietly somewhere in the background, depends on mathematics as well. The notes themselves, the frequencies of sound that your ears perceive as pitch, follow the same ratios that Pythagoras discovered when he plucked a string. The digital encoding of that music, whether it is streaming from a service or stored on a device, relies on mathematics, on the same Fourier transform that we mentioned earlier in the context of medical imaging, a technique for breaking down complex signals into combinations of simpler wave patterns. The compression that allows music to be stored efficiently and transmitted quickly relies on mathematical algorithms, on the same probability and information theory that grew out of the work of Claude Shannon in the mid-20th century. Every time you hear a song, every time you listen to a podcast, every time you hear someone's voice through a speaker, you are hearing mathematics, translated into sound. The food you ate today or will eat tomorrow was grown, processed, transported, and sold using mathematics. The logistics that get food from farms to stores, the optimization that determines the most efficient routes for trucks, the inventory management that ensures shelves are stocked, all of these are built on mathematics. The agricultural techniques that maximize crop yields, the genetic analysis that helps breed more productive plants, the weather prediction that helps farmers decide when to plant and harvest, all of them rely on mathematics, on the same calculus and probability and statistics that we have been tracing through tonight. The clothes you wear were designed using mathematics, sized according to statistical distributions of human body measurements, cut according to geometric patterns, manufactured using machines that are controlled by mathematical algorithms. The materials they are made from, the synthetic fibers that have become so common, were developed using chemistry, and chemistry is built on mathematics, on the same quantum mechanics and thermodynamics that describe the behavior of atoms and molecules. The dyes that give them color were developed using the same mathematics, the same understanding of how light interacts with matter, an understanding that depends on the wave equations that grew out of calculus. The building you are in, the room you are lying in, was designed using mathematics. The architects and engineers who designed it used geometry to determine its shape and structure, used calculus to calculate the loads that the walls and floors must bear, used differential equations to model how heat flows through the walls and how sound travels through the rooms, used probability and statistics to account for uncertainties in the materials and the forces they must withstand. The building codes that ensure its safety are based on mathematics, on the same probability and statistics that allow engineers to say with confidence that a building is unlikely to collapse, even though they cannot guarantee it with absolute certainty. The water that flows through the pipes in your walls, the water you might drink later tonight or tomorrow morning, was purified and delivered using mathematics. The treatment plants that clean the water use chemical processes that are modeled with mathematics. The pumps that move the water through the pipes are controlled by mathematical algorithms. The distribution networks that ensure water reaches every home in a city are optimized using mathematics, on the same graph theory that grew out of topology and abstract algebra. The waste that leaves your building, the water that goes down the drain, the trash that is collected, all of it is managed using mathematics. The sewage systems that carry waste away are designed using the same fluid dynamics that describe the flow of water in pipes, the same calculus and differential equations that Newton and Leibniz developed. The treatment plants that process waste use chemical and biological processes that are modeled with mathematics. The collection routes for trash are optimized using the same algorithms that were developed for logistics and transportation. The money you use, whether it is physical currency or digital transactions, depends on mathematics. The banking systems that handle your money use cryptography, and cryptography is built on number theory, on the same prime numbers that Euclid proved are infinite, on the same modular arithmetic that was developed in the 19th century, on the same computational complexity that underlies the P versus NP problem. The financial markets that determine the prices of goods and services use mathematics, on the same calculus that was developed to describe motion, on the same probability and statistics that were developed for gambling, on the same differential equations that describe the growth of populations and the spread of heat. Every time you buy something, every time you check your balance, every time you transfer money, you are relying on mathematics that was developed over centuries by people who could not have imagined the world you live in. The internet itself, the network that connects your phone to the rest of the world, is built on mathematics. The protocols that govern how data is transmitted, the algorithms that route packets across the network, the error correction that ensures data arrives intact, all of these are built on mathematics. The compression that allows data to be transmitted efficiently, the encryption that protects your privacy, the search algorithms that help you find what you are looking for, all of these are built on mathematics. The very idea of a network, of nodes connected by links, is a mathematical idea, one that was studied in abstract algebra and topology and graph theory long before anyone built a computer network. The content you consume, the videos, the articles, the posts, is shaped by mathematics. The recommendation systems that suggest what to watch next are built on the same linear algebra and probability theory that mathematicians developed over centuries. The ranking algorithms that determine what appears at the top of your feed are built on the same optimization techniques that engineers use to design bridges and airplanes. The advertising that pays for the content you consume is targeted using mathematics, on the same statistical methods that scientists use to analyze medical trials. All of this, everything we have just walked through, is happening constantly, silently, around you and inside the systems you rely on every day. Mathematics is not something that exists only in textbooks or on blackboards. It is not something that only mathematicians use. It is something that is woven into the very fabric of the modern world, into the infrastructure that keeps you safe, healthy, connected, and comfortable. It is something that you interact with constantly, whether you realize it or not. And this is where we come full circle, back to where we started tonight. Because the same mathematics that runs underneath the phone charging somewhere in your room, underneath the satellites passing overhead, underneath the electricity humming quietly through the walls around you, also runs underneath your own body, underneath your own heartbeat, underneath your own breathing. Your nervous system is constantly performing calculations, estimating distances, measuring intervals, doing arithmetic on light and sound, all without your conscious awareness. The mathematics that was developed by generations of scholars, working across cultures and centuries, is not separate from you. It is part of the world you inhabit, part of the systems that sustain you, part of the very structure of your own experience. This is the quiet truth that lies at the heart of everything we have traced tonight. Mathematics is not something that was invented by a few clever people and then imposed on the world. It is something that was discovered piece by piece by people who were patient enough to look carefully at the patterns that were already there, waiting to be noticed. It is something that grew, not because anyone forced it to grow, but because it was useful, because it worked, because it helped people solve real problems, build real things, understand real phenomena. And it continues to grow, continues to be useful, continues to work, in ways that no one could have predicted, for purposes no one could have imagined. As you lie there, letting your thoughts drift, you can let all of this settle into the background of your awareness. You do not need to remember every name or every date. You do not need to understand every proof or every equation. You only need to know that the mathematics is there, quietly running underneath everything, the same way your heartbeat is there, quietly running underneath your awareness. The same way the satellites are there, quietly running overhead, the same way the electricity is there, quietly running through the walls. And you can rest, knowing that the mathematics will continue to run, whether or not you are paying attention. The numbers will continue to count themselves forward. The equations will continue to hold true. The proof will continue to be valid. The world will continue to unfold according to the patterns that mathematicians have spent millennia uncovering, piece by patient piece, each one building on the last. Rest now if you have not already. The thread we have been following will still be here when you come back to it. The same way the numbers will still be counting, the same way the equations will still be holding true, the same way the patterns will still be waiting to be noticed. Let it all settle, the way sediment settles at the bottom of still water, the way a held breath settles when it is finally released, the way a thought settles when it is no longer being held onto. There is nothing more to do tonight. There is only this moment, and the next, and the one after that, each one unfolding exactly as it is meant to unfold. Let's rest here, in the quiet that comes at the end of a long journey, with the full weight of everything we have walked through together, settling into the background of your awareness. We have traveled from a bone with notches carved into it in a cave in southern Africa, through the clay tablets of Mesopotamia, the measured fields of Egypt, the logical proofs of Greece, the formalized zero of India, the algebra and algorithms of Baghdad, the calculus of Newton and Leibniz, the probability and statistics that grew from games of chance, the strange abstract branches of the 19th and 20th centuries, and the quiet way mathematics became woven into the ordinary fabric of everyday life. Each step along this thread was tied by a real person, working with the tools and questions available in their own particular moment, unable to see very far ahead, unable to know which parts of their work would matter and which would be forgotten. And now, as we reach the end of this telling, there is one more thing worth sitting with, one more quiet truth that emerges from everything we have traced. It is not a new idea, not a final theorem or a closing proof. It is more like a feeling, a sense of something that has been present throughout this whole journey, waiting to be noticed, waiting to settle into the space between your thoughts. The truth is this: mathematics is not something that was invented by a few clever people and then imposed on the world. It is something that was discovered piece by piece by people who were patient enough to look carefully at the patterns that were already there, waiting to be noticed. The numbers were already there, in the sense that the relationships between quantities were already true, whether or not anyone had written them down. The geometry was already there, in the sense that the angles of a triangle always summed to the same value, whether or not anyone had proven it. The calculus was already there, in the sense that the rate of change of a falling object was always described by the same mathematical relationship, whether or not Newton or Leibniz had formalized it. Mathematics is not a human invention. It is a human discovery, a gradual uncovering of truths that were always present, waiting for someone patient enough and rigorous enough to see them clearly. This is why a proof from ancient Alexandria still holds exactly as true today as the day Euclid first wrote it down. It was never about Euclid. It was never about Alexandria. It was about something that does not depend on any particular place or person or moment in history. It was about logic itself, which does not decay, does not go out of fashion, does not need updating the way so much other human knowledge eventually does. A right triangle drawn tonight has exactly the same relationship between its sides as one drawn in Alexandria over 2,000 years ago, and it will have that same relationship 2,000 years from now, in a world none of us can picture. The mathematics is not going anywhere. It does not need you to hold on to it. It will hold itself. And this is where the thread we have been following connects to something deeper, something that reaches beyond mathematics itself. The same patient attention that allowed the Sumerians to notice the usefulness of a base 60 system, that allowed the Greeks to ask not just how but why, that allowed Al-Khwarizmi to formalize step-by-step procedures for solving equations, that allowed Newton and Leibniz to see the structure hidden inside continuous change, is a quality of mind that you carry with you always. It is the quality of paying attention, of looking carefully, of being willing to follow a line of thought wherever it leads, even when it leads somewhere uncomfortable, even when it challenges what you thought you knew. This is the deeper purpose of the story we have traced tonight. Not to fill your mind with facts, not to give you a list of names and dates to remember, but to show you what is possible when a mind is willing to be patient, to be rigorous, to trust that the patterns are there, waiting to be noticed. The mathematics is not separate from you. It is part of the same world you inhabit, part of the same patterns that run through your own body, your own breathing, your own heartbeat. The same logic that underlies a proof in geometry underlies the way your nervous system processes information, the way your brain makes sense of the world, the way you distinguish between what is true and what is not. As you lie there, letting your thoughts drift, you can let all of this settle into the background of your awareness. You do not need to remember every name or every date. You do not need to understand every proof or every equation. You only need to know that the mathematics is there, quietly running underneath everything, the same way your heartbeat is there, quietly running underneath your awareness, the same way the satellites are there, quietly running overhead, the same way the electricity is there, quietly running through the walls. And you can rest, knowing that the mathematics will continue to run whether or not you are paying attention. The numbers will continue to count themselves forward. The equations will continue to hold true. The proofs will continue to be valid. The world will continue to unfold according to the patterns that mathematicians have spent millennia uncovering, piece by patient piece, each one building on the last. There is something quietly reassuring in that. The mathematics running through your own nervous system right now, keeping your heart beating in that steady rhythm, keeping your balance settled against the mattress, does not need you to understand it in order to work. In the same way, the mathematics running underneath the phone charging somewhere in your room, underneath the satellites passing overhead, underneath the electricity humming quietly through the walls around you, does not need your attention either. It simply works, the way it has worked for as long as there have been minds patient enough to look for the patterns, going back to someone, alone, in a cave, 43,000 years ago, cutting a single notch into a bone, and then another, beginning a thread that would eventually reach all the way to you, here, now, tonight. If you have drifted during this telling, that is perfectly fine. The ideas will still be here if you want to come back to them. And even if you do not consciously follow every sentence, something of this has settled into you anyway. The way sediment settles at the bottom of still water, the way a held breath settles when it is finally released, the way a thought settles when it is no longer being held onto. Something has been planted, something that will continue to grow in its own time, in its own way, without needing any further attention from you. You do not need to hold on to any of it. Let it go the way you let go of a held breath. The numbers will still be there tomorrow, and the day after that, counting themselves forward the way they always have, whether or not anyone is awake to notice. Somewhere, right now, a satellite is quietly correcting its clock for the curve of space. Somewhere, a heart is beating in a rhythm a differential equation could describe. And here, in this room, your own breathing is slowing, your own thoughts are loosening their grip on the day behind you, drifting the way a sequence drifts toward a limit, closer and closer, never quite needing to arrive, because getting close enough is already, quietly, everything. This is really what mathematics is, underneath all of the specific formulas and theorems we have walked through tonight. It is not a fixed body of facts to be memorized. It is a very long, very patient act of collective reasoning, carried out by countless individual people across an enormous stretch of time, each one testing an idea against pure logic, keeping what survived that test, and passing it forward to whoever came next. The reason it works, the reason a proof from ancient Alexandria still holds exactly as true today as the day Euclid first wrote it down, is that it was never actually about ancient Alexandria, or about Euclid himself at all. It was about something that does not depend on any particular place, or person, or moment in history. It was about logic itself, which does not decay, does not go out of fashion, does not need updating the way so much other human knowledge eventually does. And this is the quiet truth at the heart of everything we have traced tonight. Logic is not a human invention. It is a feature of the universe itself, a structure that was always there, waiting to be noticed, waiting to be understood, waiting to be used. the mathematics that describes the orbit of a planet, the flow of electricity, the rhythm of a heartbeat, the pattern of a sunflower's seeds, the distribution of prime numbers, the curvature of space itself. All of it is a reflection of the same underlying logic, the same deep structure that runs through everything, connecting the largest galaxy to the smallest particle, connecting the oldest bone with the newest phone, connecting you, in this room, to every other mind that has ever been patient enough to look carefully at the patterns and ask why. Rest now, really rest, not because you have earned it, though you have, but because rest is the final and most important part of the whole process. Rest is where what has been heard becomes what is known. Rest is where the threads that have been laid down begin to weave themselves together into something that is not just information, but understanding. Rest is where you become not just someone who has been told a story, but someone who carries that story inside them, the way the earth carries the memory of every seed that has ever fallen into it, whether that seed grew into a tree or simply returned to the soil from which it came. Let the story settle now, the way a stone settles into the bed of a river, finding the shape of the space around it without effort. And let yourself settle with it, into the darkness, into the quiet, into the simple fact of being here, in this room, at this moment, with no need to be anywhere else or anyone else or know anything other than what you already know, which is that you are safe, and you are resting, and the rest of it can wait for another time. The thread we have been following will still be here when you come back to it. The same way the numbers will still be counting, the same way the equations will still be holding true, the same way the patterns will still be waiting to be noticed. There is nothing more to do tonight. There is only this moment, and the next, and the one after that, each one unfolding exactly as it is meant to unfold. You don't need to hold on to any of it. Let it go the way you let go of a held breath. The numbers will still be there tomorrow, and the day after that, counting themselves forward the way they always have, whether or not anyone is awake to notice. Somewhere, right now, a satellite is quietly correcting its clock for the curve of space. Somewhere, a heart is beating in a rhythm a differential equation could describe. And here, in this room, your own breathing is slowing, your own thoughts are loosening their grip on the day behind you, drifting the way a sequence drifts toward a limit, closer and closer, never quite needing to arrive, because getting close enough is already, quietly, everything. Rest now. The rest of it can wait until morning, or it can simply stay here, settled, unbothered, the way it has been settling for longer than anyone has been alive to watch.